Light's journey to the absolute limit of reality. What if I told you that for a particle of light, a million-year journey and the blink of an eye are the exact same thing? To a photon, there is no such thing as time. And in its timeless journey across the cosmos, it reveals a fundamental secret about the very fabric of your reality. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The speed limit of the universe. There's a speed limit in our universe, and absolutely nothing with mass, not you, not a spaceship, nothing, can break it. But the reason why is probably not what you think. You've likely heard that as you speed up, your mass increases, making it harder to push you any faster. While that idea was a useful stepping stone, it's now seen as an outdated and confusing way to look at things. The real, mind-bending explanation is that everything in the universe is always moving through the four dimensions of spacetime at one single speed, the speed of light. Right now, just sitting there, you're hurtling through the time dimension at light speed. When you start moving through space, you have to trade some of your speed through time to do it. You can't go faster than the total speed of light because you're already maxed out. It's a bit like a car that has a total speed of 100. It can do 100 going north, or it can do 60 north and 40 east, but it can never exceed 100 total. This reframes the entire question. You're not trying to go faster. You're just trying to change the direction of your travel through spacetime. The nature of spacetime. So, what is this spacetime you're traveling through? Picture it as a four-dimensional fabric woven from space and time. When something massive like a star sits on this fabric, it creates a curve, a dip that tells other objects how to move. That's gravity. But it's also a clue to why light is so special. Photons, or particles of light, are unique travelers. They don't experience time like we do. For them, the trip is instantaneous. This is because they dedicate all of their motion to traveling through space, moving at the universe's max speed. Exactly 299,792,458 meters per second in a vacuum. But wait, what happens when light hits glass or water? It slows down. This isn't because the individual photons are hitting the brakes. The old explanation was a simple model of photons being absorbed and re-emitted, but the modern quantum view is far stranger. Think of it as a collective effect. The light wave interacts with the electric fields of the atoms in the material, and this complex dance creates a delay, an interference that slows the overall wave's progress. The photons themselves are still zipping at c in the tiny gaps between atoms, but the wave as a whole takes longer to get through. Light is a relentless traveler. Following a photon on its cosmic journey reveals it as a relentless traveler. Imagine one setting off from a distant star. It encounters black holes, galaxies, and nebulae, and each one warps the spacetime fabric, bending the photon's path. When that light ray passes near a black hole, the gravitational pull is extreme. Here's where it gets truly weird. The closer it gets to the event horizon, the point of no return, the more time seems to stretch and slow down for an outside observer. But from the photon's perspective, where time doesn't pass, it just continues its instantaneous journey along the path laid out for it by gravity. This gives us a profound realization. Light isn't just a messenger. It's a witness to the universe's entire history. Every single photon that reaches your eye carries the story of its journey, every gravitational nudge, every galaxy it has passed. The philosophical implications. Let's just pause and think about what this all means. What are the implications of something that never stops, that is always in motion? In a way, light embodies the essence of existence. It's a constant reminder that the universe isn't static. It's a dynamic, ever-changing place, and it's full of mysteries we're just beginning to understand. We often feel the weight of time, measuring our lives in days and years. But light carries no such burden. It exists in a state where the journey and the destination are one and the same. This can really challenge how we think about our own lives. If light can cross the universe without the constraints of time, what does that say about our own perceived limitations? Can we, too, learn to see beyond the immediate and the tangible? The journey of understanding. The more we learn about light, the deeper the questions about reality become. Take the idea of now. We assume that two events happening at the same time are simultaneous. But according to Einstein's theory of relativity, simultaneity is relative. If two people are moving at different speeds, they might not agree on whether two separate events happened at the exact same moment. This just adds another bizarre layer to our understanding of light. It constantly challenges our most basic perceptions and forces us to accept that our everyday experience is just a tiny slice of a much weirder reality. The cosmic connection. This all brings us back to our place in the universe. Light is the bridge that connects us to the cosmos. Every single time you look up at the stars, you're seeing light that has traveled unimaginable distances to find you. You're literally looking back in time. The light from some stars took millions or even billions of years to get here. Each twinkle is a postcard from the distant past, a snapshot of cosmic history. This connection is profound. It reminds us that we are not just living on a rock. We are participants in a grand, interconnected cosmic story. The future of light and discovery. And the journey isn't over. As we look to the future, the study of light is opening up even stranger territories. Scientists are wrestling with things like quantum entanglement and the bizarre dual nature of light as both a particle and a wave. These new frontiers are forcing us to throw out old ideas and completely reconsider what we thought we knew about the universe. The more we learn about light, the more we realize how much we have left to discover. This journey of discovery is what science is all about. Staying curious, always asking questions, and never being afraid to seek out the answers. If this journey into the nature of light blew your mind, be sure to subscribe and join our community of curious minds. And let me know in the comments, what's the most fascinating thing you've learned about light and its role in shaping our reality? Light's journey across the cosmos reveals the bizarre and mind-bending rules that govern our universe. It's a journey through physics, but also a journey into the nature of existence itself. So the next time you flick on a switch or look up at the sun, remember that you're seeing a relentless traveler, a particle that carries the secrets of the universe and the very essence of time itself. What will you discover on your own journey? The unbreakable law forbidding light from stopping. In the universe, there are rules. Some are complex, governing the slow dance of galaxies over billions of years. Others are simple, quiet, and etched into the fabric of existence itself. One of these rules applies to a single thing: light. It must always travel at a constant speed, about 299,792,458 meters per second in a vacuum. It is forbidden from slowing down, and it can never stop. This is not a suggestion. It is a fundamental condition upon which reality depends. The question of why might seem simple, but the answer takes us on a journey through the unfamiliar world of Einstein's relativity and into the quiet realm of quantum mechanics. It leads us to a truth that underpins spacetime itself. You have likely heard that nothing can travel faster than light, but it is worth taking a moment to wonder why light itself cannot travel any slower. Why can it not simply pull over? What keeps it on a perpetual journey at the absolute maximum speed the cosmos allows? By the end of this exploration, we will see not only why light is forbidden from stopping, but also why our own existence, the flow of time, and the logical consistency of the universe all depend on this one, unbreakable law. We will see that a particle of light, a photon, is a fundamentally different kind of thing than anything else we know, and that its eternal motion is not an oddity. It is perhaps the single most important feature of our reality. The paradox of a massless particle. Let's begin with a thought experiment. Imagine you could catch a beam of sunlight. Not just feel its warmth, but hold a piece of it still in your hand, a frozen, shimmering fragment of pure light. It is a beautiful image, but it is also profoundly impossible. In our universe, light is bound to perpetual motion. It is born moving at its constant speed, and it will end moving at that exact same speed. It does not accelerate. It does not cruise. It never stops. But why? To understand this law, we must first look at the thing it governs, the photon. Photons are the fundamental particles of light, the small packets, or quanta, of the electromagnetic field. And they have a strange property that sets them apart from every other piece of matter. They have zero rest mass. That phrase, rest mass, is important. You have probably heard that photons are massless, and this is true, but it is the rest part that holds the secret. Rest mass is the mass of an object when it is not moving. It is an intrinsic amount of stuff. If you are standing still, your mass is your rest mass. For a particle to be at rest, it must have a rest mass to begin with. The very concept of stopping is something that only applies to things that have this property. A photon does not. Because a photon has zero rest mass, it can never be at rest. If a photon did stop, it would have zero energy and zero momentum. It would, in effect, cease to exist. It is not just that stopping a photon is difficult. A stopped photon is a contradiction, like a silent sound. Its existence is defined entirely by its motion. This is where our intuition, built from a world of massive objects, begins to fail us. We think of speed as something added to an object. A car starts at zero and you give it speed. A ball sits in a hand at zero, and an arm gives it speed. We see speed as a property separate from the object itself. But for a photon, speed is not a property it has, it is a property it is. Its speed, C*, is as fundamental to its identity as its lack of charge. The reason that having zero rest mass means a particle must travel at this specific speed lies in one of the most elegant equations in physics, a more complete version of E equals mc squared. That version only applies to objects at rest. The complete energy-momentum relation is E squared equals pc squared plus m0c squared, squared. Let us look at this quietly. E is the total energy. P is momentum. m0 is rest mass, and c is the speed of light. This equation is like a cosmic budget for every particle. It describes how a particle can distribute its energy. A particle with rest mass, like an electron, must spend some of its energy just existing. That is the m0c squared part. The rest can be spent on motion, the pc squared part. But for a photon, the rest mass, m0, is zero. The entire m0c squared term vanishes. The equation becomes much simpler. E squared equals pc squared. If you take the square root of both sides, you get E equals pc. This simple relationship is the rulebook for a photon. It means its energy and its momentum are forever locked together, proportional to each other by the constant, c. It cannot have energy without also having momentum. A particle that obeys this rule must travel at the speed of light. For a massive particle, you can add energy to change its momentum and speed. But for a massless particle, energy and momentum are inseparable. To have any energy at all is to move at c. To slow down would be to change the value of c, which is a fundamental constant of the universe. It is woven into the geometry of reality itself. The grand illusion of slowing down. At this point, a question should arise. You may have heard that scientists have slowed down light, or that light moves slower through water or glass. This seems to contradict everything we have just established. This is one of the most common and subtle points of confusion in all of physics. The answer reveals that what we call slowing down light is one of the most beautiful and elaborate illusions in nature. Let's start with a beam of light traveling through a block of glass. In a vacuum, light travels at c. Inside the glass, its effective speed is less, perhaps 2/3 of c. The photons have not slowed down. Every single photon involved in that journey is still traveling at exactly c. What we are seeing is the result of a complex, subatomic interaction. Imagine a message being passed through a quiet crowd. Each person who carries the message moves at the same top speed. But at each handoff, from one person to the next, there is a brief, almost imperceptible pause. An observer watching from a distance would see the message itself appearing to move slowly across the crowd. Yet no individual carrier ever slowed down. This is a good analogy for what happens when light travels through a medium. The carriers are the photons, and the crowd are the atoms of the material. A photon, traveling at c*, does not just slip between the atoms. It is absorbed by an atom's electron cloud. For a fleeting moment, the photon ceases to exist as an independent particle. Its energy is stored in the atom. This state is unstable, and the atom almost immediately emits a brand new photon, identical to the first. This new photon then travels at c until it encounters the next atom, and the process repeats. So the light that emerges from the other side of the glass is not the same light that went in. It is a cascade of new photons, a chain reaction of absorption and re-emission. The individual photons are always traveling at c in the empty space between atoms. But the cumulative effect of these tiny delays makes the overall propagation of the light wave appear slower. The group velocity of the wave is reduced, but the speed of its fundamental parts, the photons, remains absolute. This is a quiet, mind-bending concept. It means that the ray of sunlight you see refracting through a prism is a reconstructed beam, a ghost of the original light built from countless microscopic interactions. The universe is performing a subtle sleight of hand, all to uphold its one unbreakable law. The photon itself never slows down. The ultimate trick: stopping light. Now we come to the experiments that seem to break the rule entirely. In the late 1990s and early 2000s, groups of physicists did something that sounded impossible. They appeared to stop light. Reports described light pulses being slowed to the speed of a bicycle, and then held still for a fraction of a second. The truth of what happened is stranger and more wonderful than that. They did not stop a photon. They transformed it. They performed a kind of quantum alchemy, changing light into matter, and then back into light again. The process is sophisticated, but we can understand it with another analogy. Imagine a message written on a piece of paper. You give this to a courier, who runs to a destination. The courier is the photon, and the paper is the information it carries. The courier can never stop running. But what if the courier could meet another person, who memorizes the message perfectly? The courier transfers the information and then vanishes. The message, however, now exists in a new form, as a memory. This person can stand still. They can wait. Then, they can write the message on a new piece of paper and hand it to a new courier, who instantly begins running. From the outside, it would look like the message was stopped. But what actually happened was a transfer of information from one carrier to another. This is almost what happens in the stopped light experiments. Scientists use a strange state of matter called a Bose-Einstein condensate, BEC. A cloud of atoms chilled to near absolute zero, so cold they behave as one single, superatom. They fire a control laser to prepare the BEC, then they fire a second probe pulse, the light they want to stop, into it. The probe pulse of light gets entangled with the atoms of the BEC. The photons and atoms combine to form a new hybrid particle. This new particle is part light and part matter. It carries all the information of the original light, but because it is now coupled to the massive atoms, it moves incredibly slowly. Then, the scientists switch off the control laser. The light component vanishes entirely. But the information it carried is imprinted onto the atoms of the beck. The photons are gone. Their ghost remains, stored as a pattern in the matter. At this point, there is no light in the condensate. There are no photons. There is only a cloud of matter holding the memory of a light pulse. After a few milliseconds, the scientists turn the control laser back on. This reverses the process. The matter imprint is read out, and it creates a brand new light pulse, an exact replica of the original, which exits the condensate, instantly traveling at speed c. So, did they stop light? No. They stopped the asterisk information the light was carrying by converting it into a different form of energy. They never had a photon sitting still. The moment the light pulse was stopped, its photons ceased to exist. And the moment it was restarted, entirely new photons were created. The law remains unbroken. The photon, a creature of pure motion, either travels at c or it does not exist at all. The cosmic necessity of an unbreakable law. We have seen how the universe enforces its speed limit for light. We have seen that a photon's lack of rest mass means it is born at speed c and can never travel at any other speed. But now we must ask the deepest question. Why? Why is this law so absolute? The answer is that the constant speed of light is the bedrock of causality. It is the law that gives the universe its logical structure. Albert Einstein's special theory of relativity is built on two postulates. The first is that the laws of physics are the same for all non-accelerating observers. The second, and most crucial for us, is that the speed of light in a vacuum, c*, is the same for all observers, no matter how they are moving. This is completely alien to our everyday experience. If you are on a train and throw a ball forward, an observer on the platform will see the ball's speed added to the train's speed. But this is not true for light. If you are on a spaceship traveling at 99% the speed of light and turn on a flashlight, you will measure that light moving away from you at c. Someone you pass will also measure that light moving at c. For this to be true, something else must be changing. That something is space and time itself. For the speed of light to remain constant for everyone, time must slow down and space must contract for moving observers. This is a physical reality, proven by experiments with atomic clocks. Here is where it connects to our stopped photon. If a photon could be at rest, it would have a point of view from which it is stationary. But Einstein's second postulate forbids this. If you could sit at rest with a photon, you would measure its speed as 0. But someone flying past you would have to measure its speed as c. This is a paradox that would break the logical structure of relativity. The universe avoids this by forbidding massless particles from ever being at rest. The implications go even deeper, to the very heart of cause and effect. The speed of light is not just the speed of light. It is the speed of causality. It is the ultimate speed limit for any information or influence to travel through spacetime. If you could send a signal faster than light, you could create effects that precede their causes. The universe would become a chaotic mess of paradoxes. The constant speed of light prevents this. It creates a clear and absolute structure for spacetime, dividing it into a past that can affect us, a future that we can affect, and a vast elsewhere that is causally disconnected from us. If the speed of light were not constant, the safeguard that protects the logical flow of time would be gone. The universe needs a supreme, unchanging speed limit to maintain order. Massless particles, like photons, are the messengers of this limit. Conclusion. So, we return to the unbreakable law. Light cannot stop. Not because it has some infinite engine, but because of what it is. A photon is a particle with no rest mass. Its entire identity is tied to motion. Its energy and momentum are locked in a perfect dance dictated by the equation E=pc. To exist is to move at c. To stop is to cease to be. The illusions we see, light slowing in glass, or being stopped in a lab, are just that. Beautiful, complex illusions. They are quiet quantum handoffs, where information is passed from photon to atom and back again, while every photon involved maintains its sacred, unwavering speed. And this law is not arbitrary. It is a pillar supporting the structure of reality. The constant speed of light is the constant of causality. It ensures that time flows forward and that causes precede effects. Light is always on the run because it is the cosmic messenger, the thread that weaves the past into the present. Its ceaseless journey is what stitches the history of the cosmos into a coherent story. If it could stop, the story would fall apart. The next time you switch on a lamp, or look up at the night sky, take a moment to appreciate what you are seeing. You are witnessing billions of tiny particles that refuse to have mass, that refuse to stand still. They are on an eternal sprint across spacetime, not because they are in a hurry, but because their motion helps define the fabric of space and time itself. They are upholding a law written not in any book, but encoded into the soul of the cosmos. The unbreakable law forbidding light from ever stopping. Why 13 billion years is 0 seconds for light? Imagine a single particle of light, a photon. It's born in the fiery heart of a star that died long before our Earth even formed. It springs into existence and begins an epic journey across the cosmos. It travels for an almost unimaginable amount of time. Let's say nearly 13.8 billion years, streaking through the expanding void, past swirling young galaxies and whirlpools of dark matter. After a journey that spans almost the entire age of the universe, it finally ends its flight by striking a detector in a telescope right here on Earth. For us, the story of this photon is an epic of cosmic proportions. But here's the truly mind-bending part, a beautiful and baffling truth at the very heart of modern physics. For the photon itself, that incredible journey happened in literally no time at all. From its perspective, the moment it was created and the moment it was absorbed were the exact same instant. So how can this be? How can nearly 14 billion years of cosmic history be compressed into 0 seconds? The answer isn't a metaphor, it's a description of physical reality, found in Albert Einstein's theory of special relativity. To get it, we have to let go of our everyday, common-sense ideas of time and space and venture into a realm where reality behaves in ways that seem impossible. We have to learn to see the universe from the perspective of light itself. You've probably heard of the twin paradox. One twin leaves Earth on a spaceship that travels close to the speed of light. The other stays behind. When the traveling twin finally returns, a shocking scene awaits. The twin who stayed home is now decades older, maybe a grandparent with gray hair, while the traveler has barely aged at all. This isn't science fiction, it's a direct consequence of the laws of physics. But what does a story about two twins have to do with a photon? Everything. The strange effect that keeps the traveling twin young is the very same principle that makes the photon's journey timeless. The key to this whole mystery can be boiled down to one single, stubborn, universe-bending fact. The speed of light is constant for everyone. And to protect that one rule, time and space themselves will warp in the most extraordinary ways imaginable. The unbreakable law. Before Einstein, our universe was Isaac Newton's universe. His laws were elegant and intuitive. In a Newtonian world, speeds add up. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20, someone on the ground sees the ball moving at 120. Simple. Obvious. And for most things in our lives, it's correct. So, in the 19th century, physicists figured the same logic had to apply to light. They imagined an invisible medium that light waves traveled through, a cosmic ether. If that were true, then as the Earth orbits the Sun, we must be moving through this ether. That means if we measure the speed of light in the direction of Earth's motion, we should get a slightly faster speed, and a slightly slower speed in the opposite direction. It was the same logic as the train and the ball. In 1887, two American scientists, Albert Michelson and Edward Morley, set out to prove it. They designed an incredibly sensitive experiment to detect this ether wind. They split a beam of light, sent the two halves in different directions, and then brought them back together. Any change in speed would create a specific interference pattern. They ran the experiment. They rotated it. They ran it again at different times of the year. And every single time, they found nothing. The result was null. The speed of light was exactly the same, no matter how they measured it. This was a huge crack in the foundation of classical physics. It made no sense. It was like throwing that ball on the train and having both you and the person on the ground measure its speed to be exactly the same. The result was so baffling that many thought the experiment had to be flawed. But it wasn't. It pointed to a deeply weird truth about our universe. This is where a young Albert Einstein entered the picture. While others tried to patch up the old theories, Einstein decided to take the result at face value. He proposed a radical new idea. What if the speed of light in a vacuum isn't relative? What if it's an absolute constant for all observers, no matter how they're moving? This simple-sounding idea has earth-shattering consequences. If you and I are moving relative to each other and we both measure the speed of the exact same beam of light, we must get the exact same number. 299,792,458 meters per second. Period. But how can that be? If I'm flying in a spaceship at half the speed of light and I turn on my headlights, a stationary observer doesn't see that light moving at 1.5 times the speed of light. They see it moving at exactly the speed of light. And even crazier, from my perspective on the ship, that beam is still moving away from me at the speed of light. For this unbreakable rule to hold true, something else has to give. If the speed of light is sacred, then our absolute notions of space and time must be flexible. They have to stretch and shrink to keep the speed of light constant for everyone. This is the core of special relativity. To maintain the constancy of light's speed, the universe sacrifices the constancy of time. And this is where our journey into the photon's timeless experience really begins. It all starts with the idea that your speed through space determines your speed through time. How motion slows time, the light clock. To get how this works, let's use one of Einstein's favorite tools, a thought experiment. We're going to build the simplest clock imaginable, a light clock. Imagine two parallel mirrors with a single photon of light bouncing between them. Each time the photon hits the bottom mirror, our clock ticks. We know the distance and we know the speed of light, so we can calculate the time for one tick. It's a perfect clock. Now, let's put this clock on a train. For a person sitting on the train, nothing has changed. The photon is just going straight up and down. The distance is the same, the speed of light is the same, so the clock ticks at its normal rate. This is the clock's proper time. But now, let's watch this clock from the platform as the train speeds by. From our stationary perspective, the clock is moving. As the photon leaves the bottom mirror, the train moves forward. So, to hit the top mirror, the photon has to travel on a diagonal path. Then, it has to travel another diagonal path to get back to the bottom mirror, which has also moved. This is the crucial moment. From our view on the platform, the photon in the moving clock has to travel a longer distance. But remember Einstein's unbreakable law. The speed of light must be the same for both of us. So if the speed is the same, but the distance is longer, what does that mean? It means from our perspective, the journey must take more time. The tick of the moving clock, as we see it, is longer than the tick of our own clock. Time itself, for the moving clock, appears to be running slow. This isn't an illusion or a trick of perception. It's a real, physical effect. A clock in motion relative to you will genuinely tick slower than your clock. This is time dilation. And it applies to all clocks, whether they're mechanical, digital, or even biological. Your own heartbeat is a type of clock. If you are on that train, your heart beats slower and you age slower, all from the perspective of the person on the platform. You wouldn't notice, of course. To you, everything feels normal. It's only by comparing your clock to one in a different frame of reference that the effect becomes obvious. Now, let's start pushing the speed. At everyday speeds, the effect is minuscule. But as we get closer to the speed of light, the consequences become dramatic. At 10% the speed of light, time on a spaceship runs about 0.5% slower. A year on the ship is a year and about 2 days on Earth. At 50% the speed of light, time on the ship is about 15% slower. For every year the astronauts experience, about 1 year and 2 months pass on Earth. At 86.6% the speed of light, time on the ship runs at exactly half the speed of time on Earth. A 1-year journey for them means 2 years have passed for everyone back home. At 99% the speed of light, a 1-year trip for them is 7 years on Earth. At 99.999% the speed of light, a single year for the astronaut is more than 2 centuries for Earth. You see the pattern. As you get closer and closer to the speed of light, time dilation skyrockets towards infinity. It's as if the universe is slowing your personal flow of time to a crawl to prevent you from ever reaching light speed. So, what happens if you become the photon? At that point, the time it takes for a single tick becomes infinite. In other words, time stops completely. For anything traveling at the speed of light, time does not pass. The human story of warped time, the twin paradox. This whole idea can feel a bit abstract. So let's make it concrete and go back to our twins, Stella and Tara. They're identical, both 30 years old. Stella, an astronaut, is about to travel to a planet orbiting Proxima Centauri, our nearest star, roughly 4.2 light-years away. Her spaceship can travel at a staggering 95% of the speed of light. From Tara's perspective on Earth, the round trip will take about 4.42 years each way. Add the 1 year Stella spends orbiting the planet, and Tara expects her sister to be gone for a total of almost 10 years. She'll be nearly 40 when she sees her twin again. But for Stella, things are very different. Because she's moving so fast, her personal clock, her watch, her ship's chronometer, her own body, is running much slower. The time dilation factor at this speed is about 3.2. So for Stella, the journey out doesn't take 4.42 years. It takes 4.42 years divided by 3.2, which is only about 1.4 years. With the return trip and her year in orbit, the entire mission for her lasts just 3.8 years. Imagine their reunions. When the hatch opens, Stella, who is now almost 34, walks out. She sees an older woman who looks remarkably like her mother. It's Tara, now almost 40. The reunion is joyous but deeply weird. One twin has lived nearly a decade, while the other has experienced less than 4 years. Both of their experiences are valid. Both of their clocks are correct in their own frame of reference. There is no single, absolute, correct time. This is the solution to the paradox. It's only a paradox if you cling to the old idea of absolute time. In Einstein's universe, the time that passes between two events depends on the path you take through spacetime. Tara took a short path through space, she stayed put, but a long path through time. Stella took a very long path through space, and to compensate, the universe forced her to take a shorter path through time. This isn't just a thought experiment. It's been confirmed. Atomic clocks are so accurate they can measure the tiny time dilation on a commercial flight. GPS satellites orbiting Earth at high speeds have to constantly adjust their clocks for this effect. If they didn't, the entire GPS system would fail within minutes, racking up errors of several kilometers every day. The twin paradox is real, and it's the key to understanding the photon's timeless journey. The ultimate limit and the photon's reality. We have undeniable proof of this happening all around us, raining down from the sky every second. This proof comes from a tiny particle called a muon. Muons are created when cosmic rays from space smash into our upper atmosphere, about 10 to 15 kilometers up. In a lab, a muon has a very short average lifespan, about 2.2 microseconds. Now, let's do some simple math. These muons travel towards Earth at about 99.8% of the speed of light. Even at that pace, in their short 2.2 microsecond lifespan, they should only be able to travel about 660 meters. Since they're created over 10 kilometers up, it seems like none of them should ever reach the ground. They should decay long before they get here. But they don't. We detect a constant shower of muons at sea level. How? The answer is time dilation. From our perspective on Earth, the muon is a tiny, fast-moving clock. Because it's traveling so fast, its internal clock is ticking much slower than ours, by a factor of about 16. So, from our frame of reference, its average lifespan is at 2.2 microseconds. It's dilated to about 35 microseconds. In this extended lifespan, it can easily travel over 10 kilometers to reach the surface. The muons raining down on us are direct, observable proof that moving clocks run slow. Now, here's where it gets even stranger. From the muon's point of view, its lifespan is still the normal 2.2 microseconds. So how does it explain reaching the ground? The other side of relativity's coin. Length contraction. Just as time dilates, space contracts in the direction of motion. For the muon, the 10 kilometers of atmosphere rushing towards it is contracted by that same factor of 16. From its perspective, the distance to the ground is only about 660 meters, a distance it can easily cover. Both viewpoints give the exact same result. Time and space are interwoven into a single fabric, spacetime. And this fabric will stretch or shrink as needed to protect the one sacred law: the speed of light is constant. Now, at last, we are ready to take the final leap to 100% the speed of light. What happens when we become a photon? As we saw, as your speed approaches, the time dilation factor approaches infinity. At the exact speed of light, time dilation becomes infinite. This means that for a photon, time stops. For the photon, its entire journey across the universe happens in a single instant. It is emitted, and in that very same moment of its own experience, it is absorbed. The 13.8 billion years that we measure simply do not exist in its frame of reference. And what about space? The entire universe, in the direction of its travel, shrinks down to a single point. The 13.8 billion light-years of distance we perceive is, from the photon's perspective, zero distance. So for the photon, its epic journey is a trip of zero distance that takes zero time. This is why you can't really talk about a perspective for a photon. The laws of relativity break down into infinities and zeros. It's like asking what's north of the North Pole. But by approaching the speed of light as a limit, we can see what reality tends towards. A place where time and distance in the direction of travel vanish completely. If bending your mind around the nature of time and space is your kind of thing, consider subscribing to join our community of curious thinkers. And if you want to see how gravity throws another wrench into our perception of time, check out our next video on how massive objects, like planets and black holes, warp time in a completely different way. Click here to watch it next. Conclusion. So, how can a journey of nearly 14 billion years take 0 seconds? The answer is a fundamental truth about our reality. Our human intuition tells us that time is a universal river, flowing at the same rate for everyone. But that intuition is wrong. Time and space are a single, dynamic entity called spacetime, and its behavior is relative. The faster you move through space, the slower you move through time. This is the universe's way of making sure that no matter how fast you chase a beam of light, it will always race away from you at the exact same speed. The universe stretches your seconds and shrinks your meters to maintain this one cosmic law. For a photon, a particle born moving at the maximum speed possible, This effect is taken to its absolute extreme. Time dilates infinitely, so it stops. Space contracts infinitely, so it vanishes. The photon's existence is a timeless, dimensionless thread connecting two points in spacetime. It experiences its entire life in a single, frozen instant. So, when we point our telescopes to the sky and capture the light from a galaxy 13 billion light-years away, we are capturing a messenger that has crossed an ocean of time without aging a single moment. It brings us an image of the infant universe, and for that messenger, its creation and its arrival are one and the same event. It is a direct link between the distant past and our present, a reminder that the fabric of our universe is far stranger, more flexible, and more wonderful than we ever could have imagined. Why calling light fast is a complete lie. We have a number for the ultimate speed limit of the universe. A figure etched into our model of the cosmos. 299,792,458 meters per second in a vacuum. We are taught to see it as a cosmic boundary, an incomprehensible velocity. We measure the vastness of space in the time light takes to traverse it. We speak of its journey from distant stars as an epoch of travel. We are, in a sense, conditioned to believe that light is fundamentally, unequivocally, fast. But this may be a profound misunderstanding, a convenience of language that obscures a deeper and far more counterintuitive reality. The truth is that from its own frame of reference, light does not travel at all. It experiences no passage of time. It covers no distance. It is emitted and absorbed in the same instant. So, if light itself is, in a way, stationary, then what is the speed of light, the speed of? The answer forces us to look again at the very nature of motion, time, and the fabric of reality itself. What we call the speed of light is not really about light. It is the speed of causality. It is the tempo of the universe. This is a journey to dismantle the idea of light as a fast object. We will explore why our intuition about speed breaks down as we approach this cosmic constant, and why nothing with mass can ever reach it, not because it's too fast, but because the very attempt would require infinite energy. In the end, we will find that the speed of light is not a speed, but a fundamental property of spacetime, a baseline against which all change is measured. Light isn't the fastest thing in the universe. It is the universe's unmoving foundation. Consider our fastest machines, capable of moving at hundreds of miles per hour, blurring the world into a stream of color. Now, consider a beam of light. In the time it takes to blink, that beam can circle the Earth more than 7 times. It crosses the distance from the Sun to the Earth in about 8 minutes. The comparison feels absurd, our technological pinnacles rendered as snails in a cosmic race. But here is the paradox at the heart of our exploration. What if, for the photon itself, the massless packet of energy that forms that beam, the entire journey takes no time at all? 0. For the photon, there is no departure and arrival, only a single, timeless instant of existence. It is emitted and it is absorbed in the same moment. So how can a thing that experiences no time possess a speed? Speed is distance divided by time. If time is 0, the equation dissolves. This is not merely a mathematical curiosity, it is a signpost, pointing toward a radical new conception of the cosmos. The crumbling of common sense. Our entire conception of speed is built on our experience in a world of mass and momentum. We understand speed as a relative concept. A person walking on a train has a speed relative to the train, and a different speed relative to the ground outside. Speeds simply add and subtract. This framework, known as Galilean relativity, is the intuitive physics that governs our terrestrial experience. For centuries, it was assumed light must behave this way. Physicists of the 19th century imagined a luminiferous ether, an invisible substance that was thought to fill all of space, serving as the medium for light waves much as air serves as the medium for sound. If this ether existed, then the Earth's movement through it should create a detectable ether wind. The speed of light measured in the direction of Earth's motion ought to be different from the speed measured against it. In 1887, Albert Michelson and Edward Morley designed an experiment to find it. They used a device called an interferometer, which splits a beam of light, sends the two halves on perpendicular journeys of equal length, and then recombines them. If one beam were slowed by the ether wind, the two waves would be out of sync upon their return, creating a distinct interference pattern. They floated the entire apparatus in mercury to allow for smooth rotation, testing every possible orientation. They ran the experiment. They rotated it. They waited for different times of year, when the Earth's orbital velocity pointed in different directions. And they found nothing. No difference. The speed of light remained stubbornly, inexplicably, the same. This was one of the most important null results in the history of science. It defied all logic. It was as if a person on a train shone a flashlight forward, and both they and an observer on the ground measured the light moving at the exact same speed. How could motion not be relative? It took Albert Einstein to elevate this strange experimental result into a core principle of the universe. He proposed that the speed of light in a vacuum is constant for all observers, regardless of their own motion. This simple postulate, born from the beautiful failure of the Michelson-Morley experiment, became the foundation of his theory of special relativity. And its consequences begin to unravel our idea of light being fast. For the speed of light to be constant for everyone, other things must be relative. Those things are space and time. For a moving observer, time slows down and distances contract in the direction of motion, time dilation and Lorentz contraction. These are not mathematical tricks, but real, physical effects. The universe warps space and time for moving observers in just such a way as to preserve the constancy of light speed for everyone. This brings us back to the number 299,792,458 meters per second. It feels like a discovered property of light, but it is a human construct. In fact, since 1983, the meter is literally defined * by the speed of light. A meter is the distance light travels in 1,299,792,458 of a second. We did not measure the speed of light to be this number. We fixed it at this number and used it to define our unit of length. The speed of light is no longer a quantity to be measured, but a standard to be used. When a value becomes so fundamental that we use it to define our other units, it suggests this is more than just a velocity. It hints that this speed is playing a much deeper role in the architecture of reality. The speed of cause and effect. If the speed of light isn't about light, what is it about? A more accurate name for this constant, C*, is the speed of causality. Causality is the principle that a cause must precede its effect. A switch is flicked, and then a light turns on. A star explodes, and then we see the supernova. Without this ordering, the universe would be a chaos of paradoxes. The constant c is the maximum speed at which any cause can propagate through space to create an effect. It is the speed at which information, any interaction, any force, any signal, can travel from one point to another. Consider a long, perfectly rigid rod stretching from Earth to the Moon. If you push one end, the other end does not move instantly. The information of your push travels down the rod as a compression wave, from atom to atom, at the speed of sound in that material. The effect is not instantaneous. Now, let us replace the rod with the fabric of spacetime itself. When a massive object moves, it creates a disturbance in the gravitational field that propagates outward as a gravitational wave. That wave travels at c. When a charged particle is disturbed, it creates a ripple in the electromagnetic field that propagates as an electromagnetic wave, which is light. That wave also travels at c. Disturbances in the electromagnetic field, light, propagate at c. Ripples in spacetime itself, gravitational waves, also travel at c. And within the quantum realm, The massless gluons that bind quarks together also move at this speed, even if the strong force itself is confined to the infinitesimal scale of the atomic nucleus. Light doesn't just happen to travel at the cosmic speed limit. As a disturbance in a fundamental field, it is a manifestation of that limit. It is massless, and so it must travel at the one and only speed the universe allows for the propagation of information through a vacuum. This is why nothing with mass can ever reach the speed of light. As an object is accelerated, its kinetic energy increases. But according to special relativity, that energy also increases its relativistic mass. It becomes harder and harder to accelerate as it gets faster. As its velocity approaches c*, the energy required to push it further approaches infinity. Since infinite energy is not available, the speed of light is an impossible destination for any object with mass. The speed limit is not like one on a highway, which could be broken with a powerful enough engine. It is a fundamental barrier woven into spacetime. It is less that light is too fast for us to catch, and more that mass itself anchors an object in space and time, preventing it from ever achieving a state of timeless, placeless existence, a state reserved for the massless. This can lead to apparent paradoxes. If you sweep a laser beam across the face of the moon, the spot of light can appear to move from one side to the other much faster than c. But no physical object has broken the limit. The spot is a series of individual photons, each traveling from the laser to the moon at exactly c. No information has been sent from one side of the moon to the other. A shadow, which is the absence of light, can also be made to move faster than c*, but a shadow is not a thing. The only true violation would be to send matter or a signal carrying information faster than c*, which would allow an effect to precede its cause. The fact that we have never observed such a violation is among the strongest evidence that c is the absolute speed of causality. As we venture further, we must leave our own perspective behind entirely and try to understand the universe as the mathematics suggests it appears to light itself. It is a journey that challenges the foundations of our intuition. For those who wish to continue these explorations into the strange architecture of reality, following our work ensures you will not miss where the path leads next. The unmoving baseline. We must now confront the most bizarre consequence of all. What does the universe look like from the perspective of a photon? Of course, a photon has no consciousness, and in the strict language of physics, it has no valid rest frame from which to have a perspective. But if we follow the mathematics of relativity to its logical endpoint, a strange and powerful picture emerges. As an object with mass approaches the speed of light, two things happen. First, from its point of view, time dilates toward infinity. At 99.9999% the speed of light, time for the traveler passes over 700 times slower than for a stationary observer. At the speed of light, the math suggests that time stops completely. From the moment a photon is emitted to the moment it is absorbed, zero time has passed for it. Second, in the direction of travel, the universe contracts. As one approaches c*, the distance to a destination shrinks towards zero. For a photon traveling at the speed of light, the distance between its origin and its destination is zero. So, from this limiting frame, a photon travels zero distance in zero time. The very concepts of distance and duration, the building blocks of speed, cease to apply. Light does not journey through spacetime. Its existence is a single, point-like event that connects two different parts of spacetime. It is a relationship, not a journey. This is the ultimate reason calling light fast is a misnomer. Speed measures movement through space over time. Light does neither. In many areas of advanced physics, scientists use natural units, where they simplify equations by setting fundamental constants, like c*, equal to 1. This is a profound statement. By setting c equals 1, physicists declare that time and space are, in a sense, the same kind of thing, convertible into one another. When c equals 1, speed becomes a dimensionless number between 0 and 1. An object at rest is 0. An object moving at half the speed of light is 0.5. And a massless particle, like a photon, moves at exactly 1. There is nothing faster than 1, because 1 represents the total possible motion through spacetime. One way to conceptualize this is to imagine that everything in the universe is constantly moving through spacetime at a single, constant speed, c. Your velocity is a four-dimensional vector, with components in the 3 dimensions of space and the 1 dimension of time. The total length of this four-velocity vector is always c. If you are at rest in space, your velocity vector points entirely in the time dimension. All your motion is through time. You are aging into the future at the maximum possible rate. When you begin to move through space, you divert a portion of your motion from the time dimension to the space dimensions. Because your total motion must remain c*, your movement through time must slow down. This is time dilation. The faster you move through space, the slower you move through time. A photon, being massless, has no motion through the time dimension at all. Its velocity vector is pointed entirely through the dimensions of space. It does not move through time. It is static in time. This is the deeper truth. We are not slow and light is not fast. We are all traveling through spacetime at the exact same rate. The only difference is the direction. We, as massive beings, are compelled to travel mostly through time. Light, being massless, travels exclusively through space. Light is not a race car. It is the unmoving road. It is the baseline of existence against which motion is measured. Calling it fast is like looking at the floor and calling it down. The floor is not just down, it is the reference that defines up. In the same way, the speed of light is not just fast, it is the reference that gives meaning to slow. Conclusion. We began with a familiar constant, the speed of light. We end with a picture that is nearly its opposite. Light does not race across the cosmos. From its own strange, timeless, and placeless frame of existence, it does not move at all. The number we call the speed of light is a property of spacetime itself. It is the speed of causality, the rate at which the universe communicates with itself, a law that shields reality from paradox. It is the reason we, as beings of mass, are carried along the river of time, unable to achieve the timelessness that would require infinite energy. By reframing our view, we see that everything, from a sleeping animal to a distant galaxy, travels through spacetime at the exact same speed, c. The difference is only in direction. We travel almost entirely through time. Light travels entirely through space. So, the next time you see the light from a lamp or a star, remember what you are witnessing. Not just something moving incredibly fast, but a consequence of the universe's unmoving baseline. You are seeing the speed of cause and effect, the unchanging heartbeat of reality itself. A reality where light does not race, but simply is, the motionless thread connecting all events, weaving together the grand tapestry of the cosmos. And our perception of it as fast is perhaps the greatest illusion of all. Why space and time bend for light? For most of the time humans have existed, our world has been a slow-moving place. Our perception of reality, our deepest feelings for how the universe works, have been shaped by experiences at quiet speeds. We walk, we run, we move in cars and planes. And in this world, the rules seem clear and logical. We imagine space as a fixed, invisible stage. Whether you are standing still or flying in a jet, a meter is a meter. The stage does not change simply because you are moving across it. We can call this idea absolute space. And then there is time. We imagine time as a universal river, flowing at the same rate for everyone, everywhere. A single cosmic rhythm, marking the seconds of the universe. 1 second for you is 1 second for a person on the other side of the planet. This is absolute time. These two ideas, absolute space and absolute time, were the foundation of physics for centuries. They were written down by Isaac Newton, and they simply make sense. Think of it with a simple analogy. Imagine you're on a train moving at 50 miles per hour. You throw a baseball forward at 100 miles per hour relative to the train. For someone standing on the ground, the math is simple addition. They would see the baseball moving at 150 miles per hour. This is how we believe the world should work. It is intuitive, but there is a problem. A deep one. This simple, logical framework begins to dissolve when you stop throwing baseballs and start observing light. When you deal with light, the universe reveals that our common sense is a simplified interface for a reality that is far more profound than we might have imagined. The rules our minds have learned are incomplete, and to understand the real rules, we have to start with the one thing in the universe that appears to be truly absolute. If this kind of calm exploration into the nature of reality helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a forest, or somewhere quiet in between, feel free to share where you're watching or listening from. The unbreakable law. At the start of the 20th century, a young patent clerk named Albert Einstein was considering a deep conflict between two pillars of physics. The first pillar was the principle of relativity, an idea that had been around since Galileo. It states that the laws of physics are the same for anyone who is moving at a constant speed. If you are in a windowless train car on a perfectly smooth track, there is no experiment you can do to tell if you are moving or standing still. Everything behaves normally. Einstein agreed with this part. The conflict came from the second pillar, the physics of light. In the 1860s, the physicist James Clerk Maxwell had unified electricity and magnetism into a single set of equations. But hidden within his mathematics was a startling prediction. Light, as an electromagnetic wave, must always travel at a specific, constant speed in a vacuum. That speed, which we call c*, is precisely 299,792,458 meters per second. A constant speed. Not constant relative to its source, but just constant. For everyone. This was the part that changed everything. Let's return to our train. According to Newton, speeds add up. But according to Maxwell, light does not follow those rules. If you are on that train moving at 50 miles per hour and you turn on a flashlight, you will measure the light's speed as c. But what about the person on the ground? Intuition says they should see the light moving at c plus 50 miles per hour. Maxwell's equations said no. They would also measure the speed of that same light beam as exactly c. It does not matter if you are rushing toward the light source or away from it. The speed of light you measure is always c. This was a fundamental problem for classical physics. It did not seem to make sense. How could two observers moving relative to each other both measure the same beam of light traveling at the same speed? Physicists in the late 19th century were so troubled by this that they proposed the universe was filled with an invisible substance called the luminiferous ether. Light, they argued, traveled at a constant speed relative to this ether. But in 1887, a precise experiment by Albert Michelson and Edward Morley was designed to detect this ether wind. They found nothing. No matter which way they pointed their instruments, the speed of light was quietly, stubbornly constant. The ether did not seem to exist. This is where Einstein's thinking came in. Where others tried to make the constant speed of light fit into the old rules of absolute space and time, Einstein took a different step. He proposed that the puzzle was not a puzzle at all. He suggested that the unbreakable law was the constancy of light's speed. If all experiments showed it to be true, then it must be true. And if that meant our understanding of space and time was incomplete, then space and time themselves had to be flexible. This slow correction tells an important story. Not just about light, but about how science works. Understanding did not fail by getting it wrong. It worked with incomplete evidence, revised ideas as new data appeared, and gradually converged on a better explanation. This was the birth of special relativity, based on two simple postulates. 1. The laws of physics are the same for all observers in uniform motion. 2. The speed of light in a vacuum is the same for all observers. From these two ideas, a new universe would begin to reveal itself. A universe where time could slow and space could shrink, all to preserve that one cosmic speed limit. The price of motion. If we accept that the speed of light is the one thing that does not change, the consequences that follow stretch the idea of what reality can be. The first and most famous of these consequences is that time itself is not absolute. The faster you move through space, the slower you move through time relative to someone who is not moving with you. This is not a metaphor. It is a physical reality called time dilation. To understand why this must be true, we can use a thought experiment. The most famous one for explaining time dilation is the light clock. Imagine a simple clock made of two mirrors, facing each other. A single particle of light, a photon, bounces between them. Every time the photon hits the bottom mirror, the clock ticks. The distance is fixed, and the photon's speed is always c. So, this clock ticks at a perfectly regular rate. If you are in a room with this clock, the photon is just going straight up and down. But now, let's put that same clock on a transparent spaceship that flies past me at a very high speed. I am standing still, watching it go by. From my perspective, the clock is moving horizontally. For the photon to go from the bottom mirror to the top, it can no longer travel straight up. The top mirror moves to the right as the photon travels. So, from my viewpoint, the photon has to travel a longer, diagonal path. Here, the new understanding reveals itself. We have established the universe's unbreakable law. The speed of light is constant for all observers. For me on the ground, that photon is still traveling at speed c. But I see it traveling a longer distance for each tick than you do on the ship. If speed equals distance divided by time, and the speed is fixed at c*, but the distance for one tick is longer from my perspective, what does that imply? It means the time it takes for that tick to happen must also be longer. From my stationary point of view, the moving clock is ticking slower than an identical clock sitting next to me. This is not a mechanical error. It is the fabric of time itself that has stretched. For the person on the spaceship, everything feels normal. Their heart beats at its normal rate. Their clock is ticking just fine. They would not notice any change. But to me, the outside observer, their time is passing more slowly. Time itself is relative. This is one of the most tested concepts in physics. We see evidence of it all around us. A classic example is the muon, a subatomic particle created when cosmic rays enter our upper atmosphere. Muons are unstable and have a short half-life of about 2.2 microseconds. If time were absolute, even at nearly the speed of light, most muons would decay long before they could travel the many kilometers down to Earth's surface. We should not detect them here in large numbers. But we do. We detect them all the time. The muons travel at about 99.5% the speed of light. From our frame of reference on Earth, their internal clocks are ticking so slowly that their lifespan is extended by a factor of about 10. This gives them enough time to survive the journey. Time dilation is the reason they can make it. An even more practical example is the Global Positioning System, or GPS. The GPS network relies on satellites orbiting Earth at high speeds. These satellites have precise atomic clocks. Because they are moving so fast relative to us, their clocks experience time dilation and run slightly slower than clocks on Earth, by about 7 microseconds every day. Engineers must correct for this relativistic effect. If they did not, your GPS would become useless, accumulating errors of several kilometers each day. The amount of time dilation is described by the Lorentz factor. The math is not essential, but what it tells us is. At everyday speeds, the effect is almost zero. But as your speed gets closer to the speed of light, the effect grows. At 50% the speed of light, time for you is passing about 15% slower than for a stationary observer. At 99% the speed of light, for every 7 years that pass for a stationary observer, only 1 year passes for you. As your velocity gets closer to C*, the effect approaches infinity. For an object moving at the speed of light, from an outside perspective, time would stop. This is the price of motion. To hold the speed of light constant, the universe requires faster moving objects to pay with the currency of time. The shrinking universe. So, time bends. It stretches to ensure that light always travels at c. But time is only one part of the story. What about space? If the unbreakable law can warp time, it must also have a profound effect on distance. This second consequence of special relativity is called length contraction. The theory states that for an observer, a moving object will appear shorter in its direction of motion than when it is at rest. Like time dilation, this is not an illusion. The fabric of space is being compressed. To understand this, let's return to the muon. From our perspective on Earth, the muon survives its journey because its internal clock slows down, giving it more time. We see it travel a long distance, but we also see its time stretch to compensate. Now, let's switch perspectives. Imagine you could ride on the muon. From its frame of reference, there is no time dilation. Its internal clock is ticking normally. Its lifespan is still just 2.2 microseconds. So, from its own perspective, how does it travel the entire distance from the upper atmosphere to the ground? The answer is that from the muon's point of view, the distance is not that long. The Earth's atmosphere is rushing up towards it at 99.5% the speed of light. Because of this motion, the space between the upper atmosphere and the ground has been compressed. It has shrunk. The journey that we on Earth measure as many kilometers, the muon measures as only a few hundred meters. A journey it can complete in its short lifespan. This is the quiet, elegant symmetry of relativity. Both observers, us on Earth and the rider on the muon, agree on the final event. The muon reaches the ground. But we disagree on the reason. We claim its time stretched. The muon claims the distance shrank. Both are correct. Both are valid descriptions of the same reality, seen from different frames of reference. This reveals that space and time are not separate. They are linked in a single, four-dimensional structure called spacetime. And this fabric is not a static background. It is dynamic. When you move through it, it can stretch and compress in different ways for different observers, all to ensure that the one golden rule, the constant speed of light, is never broken. Imagine a spaceship that is 100 meters long on the launch pad. You fly past a space station at 99% the speed of light. For you, inside the ship, nothing has changed. It is still 100 meters long. But for the people on the station watching you, your ship will not be 100 meters long. They would measure your ship to be compressed in its direction of motion, appearing only about 14 meters long. It would look flattened. Meanwhile, from your perspective, your ship is fine, but the space station you just passed would look incredibly squashed to you. Space itself is relative. The universe changes its shape depending on your motion. This is a necessary adjustment. Spacetime must bend and warp in these specific ways, dilating time and contracting length together, for the speed of light to remain constant for everyone. The ultimate speed limit. The universe performs these contortions of time and space to protect the constancy of light's speed. This leads to a final question. Why can't we go faster than light? The answer is that the speed of light is a fundamental feature of the geometry of our universe. Going faster than light is not like breaking the sound barrier. It is more like trying to travel north of the North Pole. The concept itself is not coherent within our reality. Let's bring all the pieces together. We have time dilation, length contraction, and one more piece: relativistic energy. Einstein's equation, E equals mc squared, tells us that mass and energy are deeply connected. When you push on an object, you add kinetic energy. According to Einstein, this added energy also adds to the object's effective mass, making it harder to push further. At slow speeds, this increase is infinitesimally small. But as an object with mass approaches the speed of light, the effects become enormous. The same Lorentz factor that governs time and space also governs this increase in energy. Let's look at what this means for a traveler approaching light speed. First, time dilation asterisk. From a stationary perspective, time for the traveler would slow to a near standstill. If they could reach the speed of light, their time would stop completely. An eternity for the universe would pass in a frozen moment for them. Second, length contraction asterisk. From the traveler's perspective, the universe in their direction of motion would shrink. If they could reach the speed of light, the length of the universe in their direction of travel would contract to zero. The start and end of their journey would exist at the same place, at the same time. The idea of travel would become meaningless. Third, relativistic energy asterisk. As the traveler accelerates, their effective mass increases. At 99% the speed of light, they are already about 7 times harder to accelerate than they were at rest. To get to 99.99%, you have to push against a mass that is 70 times greater. As you try to push them that final fraction closer to *c*, their resistance to acceleration approaches infinity. To accelerate an infinitely massive object requires an infinite amount of energy. There is not an infinite amount of energy in the universe, so it is physically impossible for any object with mass to reach the speed of light. The speed of light is the universe's ultimate horizon. It is a boundary woven into the geometry of spacetime itself. For anything with mass, like us and our ships, we are confined to the sublight realm. Only massless particles, like photons, can and must travel at this speed. For them, it is not a limit to be reached, but their natural state. Going faster than light would also break the logical structure of the universe, causality. The principle that a cause must always happen before its effect. If you could travel faster than light, you could create scenarios where an effect happens before its cause. The universe protects its own logical consistency by making the speed of light an absolute boundary. Conclusion. So we return to where we began, with our simple picture of the world. A world of fixed rulers and universal clocks. And we see now that this view is not wrong, but incomplete. It is a local approximation, a story we tell ourselves in the slow lane of the cosmos. The true picture is quieter and more profound. We started by asking why space and time bend for light. And the answer we found is that they must. Faced with the one absolute truth of the universe, that the speed of light is constant for everyone, it is space and time themselves that must be flexible. They are not the stage for existence, they are dynamic actors, twisting and warping to uphold that single law. Time slows down, distances shrink, and energy requirements become infinite, all as consequences of this one fact. Light is not simply moving through the universe. The universe is constantly reshaping itself around light. The next time you look up at a star, remember what you are witnessing. You are seeing the arrival of photons that have traveled across vast distances, flawlessly obeying this one strange and quiet rule. Every particle of light is a messenger from a reality where time and space are not what they seem, waiting patiently for understanding to catch up. Why you can never actually touch a ray of light. There are things we can see, but never seem to reach. A reflection in a still lake, which dissolves the moment our fingers break the surface. A rainbow, always in the distance, its shimmering arc a perfect illusion of place. These are quiet frustrations, little games of perception. But the universe has a far more profound, more fundamental untouchable. It is not an illusion, and it's not a trick of the eye. It is the fastest, most elemental thing that exists, a ray of light. You can feel its warmth on your skin. You see the world by its grace. Our existence is bathed in its ancient glow. But we can never truly touch it. Not in the way we mean. We can never reach out and match its pace, to travel alongside a photon and see the universe from its perspective. It's as if a strange, quiet rule were in place. A rule that suggests the faster something with substance tries to move, the more it resists that movement. This isn't just an idea. This is, in a very real sense, what happens to every object with mass as it tries to accelerate through the cosmos. The universe has a line drawn in the sand, a speed so absolute that it seems to define reality itself. And the reason we can't cross it, the reason we can't touch a beam of light, has little to do with the quality of our engineering and everything to do with the fundamental nature of space, of time, and of existence itself. Welcome. If this kind of calm exploration into the rules of the cosmos helps you unwind, consider liking the video and subscribing. And wherever you are right now, feel free to share where you're watching or listening from. Today, we're going to gently unravel this cosmic rule, focusing not on the equations, but on the ideas behind them. It's a journey to understand why the speed of light isn't just a number, but perhaps the ultimate law of the land. A law that makes everything else possible. The character of light. Before we can understand why we can't catch light, we have to understand what it is we're chasing. For a long time, we thought of it simply as a wave, a ripple in some unseen, universal ocean called the luminiferous ether. Then, discoveries showed it was also a particle, a tiny packet of energy called a photon. The truth, as it so often is in physics, is more complex. It's a quantum phenomenon that behaves like a wave when observed one way, and like a particle when observed another. For our purposes, let's focus on the photon. A photon is a curious thing. It is born in an instant, leaping from an excited electron in a distant star, or from the filament in a light bulb. From the very moment of its creation, it travels at one speed and one speed only. C*, the speed of light. It doesn't accelerate. It is born at full speed, and its journey ends at full speed when it strikes another particle, perhaps a molecule in your retina, and is absorbed. The speed it travels at is exact, 299,792,458 meters per second in a vacuum. This number isn't just a measurement, it has become a definition. Since 1983, the meter itself is officially defined as the distance light travels in 299,792,458 of a second. We reached a point where our measurements were so consistent that it made more sense to use light as the ultimate ruler. We have defined the speed of light to be a constant, and observations suggest it hasn't measurably changed in over 13 billion years. To give that speed some context, an object moving that fast could circle the entire Earth more than 7 times in a single second. The light from our sun takes about 8.3 minutes to make the 150 million kilometer journey to Earth. The starlight you see in the night sky is an echo, a postcard from a past that is, in some cases, thousands or even millions of years old. But here we find the quiet detail that underpins the entire idea. This speed isn't just the speed of light. It appears to be the speed of reality itself. It is the maximum speed at which any cause can create an effect. It is the speed limit for information. Nothing, no signal, no influence, can travel through space faster than c. And light travels at this speed for a simple, profound reason: it is massless. It has no inertia. It is pure energy in motion, and so it travels at the maximum speed the universe allows. Everything else, everything with even a whisper of mass, is destined to fall short. And that includes us, the world of mass. Now let's turn to the other side of this story, the world of matter. The world of mass. In school, we learn that mass is the amount of stuff in an object. In physics, it has a more precise meaning. Mass is an object's resistance to a change in its state of motion. We call this inertia. It's an intuitive idea, Pushing a bicycle into motion is easy. Pushing a car is difficult. Pushing a freight train is nearly impossible. The train has more mass, so it has more inertia. It resists the push more stubbornly. This relationship was described by Sir Isaac Newton in his second law of motion. Force equals mass times acceleration. For centuries, this was our understanding of motion. In the world we experience every day, it works almost perfectly. If you want to make something go faster, you apply a continuous force. In this Newtonian view, there's no speed limit. If you build a powerful enough rocket, you should eventually be able to go as fast as you want. But toward the end of the 19th century, an observation was made that didn't quite fit this model. Physicists were exploring the nature of light. If light was a wave traveling through a cosmic ether, then its measured speed should change depending on how we are moving through that ether. Just as a boat measures a different speed for waves depending on whether it's moving with or against the current, our planet, moving through this supposed ether, should measure a different speed of light in different directions. In 1887, two physicists, Albert Michelson and Edward Morley, set out to measure this difference. They designed a sensitive instrument that could detect this ether wind. They set up their experiment, ran it, checked their results, and found nothing. There was no change. The speed of light was exactly the same, no matter which direction they pointed their device. This null result became one of the most important observations in the history of science. The universe was not behaving as the models predicted. It was whispering a secret. The speed of light is not relative. It is absolute, constant for all observers, no matter how they are moving. This simple fact suggested that our understanding of space and time might be incomplete. It suggested a need for a new way of thinking. And that revolution in thought came from a young patent clerk named Albert Einstein. Einstein's revolution. In 1905, Albert Einstein published his theory of special relativity, a theory built on two simple, foundational ideas, or postulates. The first is the principle of relativity. The laws of physics are the same for everyone in uniform motion. This is familiar to us. If you're on a perfectly smooth train and you throw a ball in the air, it behaves just as it would if you were standing on the ground. All steady motion is relative. The second postulate was the radical one, inspired by the Michelson-Morley experiment. The speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the light source. Let's pause and think about what this implies. It challenges our everyday experience of speed. If you are driving on a highway at 50 miles per hour and another car passes you doing 70, you see their speed relative to you as 20 miles per hour. With light, this rule seems to break. If you are in a spaceship traveling at half the speed of light and you turn on your headlights, you don't see the light moving away from you at half the speed of light. You see it moving away at the full speed of light. And someone standing still on a nearby planet also sees that same light moving at the full speed of light, see. This seems like a logical puzzle. How can something move at the same speed relative to two different observers who are moving at different speeds themselves? Einstein realized that for this to be true, for the speed of light to be the one absolute constant, then other things we thought were absolute must be relative. Those things were space and time. He realized that space and time are not separate. They are interwoven into a single, four-dimensional fabric, spacetime. And our movement through this fabric involves a quiet trade-off. Everyone is always traveling through spacetime at the speed of light. If you are sitting still, you are traveling through the time dimension at maximum speed. But the moment you start to move through space, you divert some of your speed from the time dimension. The faster you move through space, the slower you move through time relative to a stationary observer. This is a physical reality called time dilation. If you were on a spaceship traveling at 99% the speed of light, your clock would tick noticeably slower than a clock on Earth. At the same time, the universe would appear to change its shape for you. The distance in your direction of motion would seem to shrink. This is called asterisk length contraction. The vast expanse of space between two stars would, from your perspective, become shorter. These two effects, time dilation and length contraction, are the universe's way of ensuring the speed of light is constant for everyone. Your measurements of length and time literally change with your velocity, so that when you measure a passing beam of light, it always clocks in at exactly 299,792,458 meters per second. This was the new world that Einstein unveiled. A world where our watches and our rulers are flexible, stretching and shrinking to preserve the one true constant, the speed of light. Energy, mass, and motion. So, time slows down and space contracts. But there is another, more formidable barrier that rises up to block the path to the speed of light. This is where we come back to Einstein's most famous equation, E equals mc squared. We usually hear this equation in the context of how a small amount of mass can be converted into a tremendous amount of energy. But the equation works both ways. It says they are two sides of the same coin. Energy and mass are equivalent. Think about what happens when you accelerate an object. You are putting kinetic energy, the energy of motion, into it. In Einstein's universe, that added energy also adds to the object's mass, or more precisely, its inertia. As an object moves faster, it becomes more resistant to further acceleration from the perspective of a stationary observer. At the speeds we're used to, this increase is infinitesimally small. But as you approach the speed of light, the consequences become profound. Imagine a hypothetical spaceship. On the launch pad, it has a certain mass. As we fire the engines and accelerate to 50% of the speed of light, it has taken a colossal amount of energy, and its effective mass has already increased. It is now harder to accelerate further. If we push the engines harder, fighting our way up to 90% of the speed of light, we would find its mass has more than doubled. It now resists our push like a much larger ship. As we try to get closer and closer, say to 99% of the speed of light, its mass would be over 7 times its original value. That last gain in speed required fighting against an object that was effectively getting heavier and heavier. You can see the pattern. The closer you get to the speed of light, the more the energy you add is converted not into speed, but into this relativistic mass. You are fighting against your own growing inertia. The mathematics shows that to reach that final, infinitesimal step to 100% the speed of light would require an infinite amount of energy to overcome an infinite resistance. The universe does not have an infinite amount of energy to give. Therefore, an object with mass can never reach the speed of light. It's not a technological problem to be solved. It appears to be a fundamental law of physics. We are trapped in a chase where we can get closer and closer, but never arrive. We can't touch the ray of light, because the faster we run, the more the universe resists. The photon's experience. We've established that for us, creatures of mass, reaching the speed of light is impossible. But this raises a curious question. What is the universe like from the perspective of something that actually travels at the speed of light? Here, we must be careful. The laws of special relativity, the very equations that describe these effects, break down at exactly c. They produce infinities and undefined values. This tells physicists that a photon doesn't have a frame of reference in the way we do. We cannot truly stand in a photon's shoes. But we can ask what happens as we get closer and closer to that ultimate speed. The answer is one of the more unusual ideas in all of physics. As you go faster, your time slows down relative to an outside observer. As you get infinitesimally close to the speed of light, this time dilation factor stretches towards infinity. This means that for a photon, time does not pass at all. From the moment a photon is emitted from a star a billion light-years away to the moment it is absorbed by your eye, zero time has elapsed for the photon itself. Its birth and its death are, from its perspective, simultaneous. And what about length contraction? As you approach the speed of light, the universe shrinks in your direction of motion. At the exact speed of light, the distance between its point of emission and its point of absorption becomes zero. The entire universe, in its direction of travel, is flattened into a single plane. If we put these two ideas together, from a photon's point of view, it experiences no time and no distance. It is emitted and absorbed in the same instant, and it crosses the entire universe without traveling any distance at all. It is, in a very real sense, everywhere along its path at once. This is why a photon can't have a point of view. Experience requires time. Observation requires space. A photon has neither. It exists on a path through spacetime where time and space have ceased to have their familiar meaning. This gives us the deepest reason yet for why we can never touch a ray of light. To travel at speed c is to leave our universe of space and time behind. The order of events. There is one final, important reason why the speed of light must be an absolute limit. This reason is less about energy and more about logic. It's about preserving the fundamental principle of cause and effect. We live in a world governed by causality. You flip a switch, cause, and a light turns on, effect. A cause always precedes its effect. This arrow of time, this ordered sequence of events, is what makes the universe comprehensible. The speed of light is the enforcer of this law. Because no information can travel faster than light, it ensures that an effect can never happen before its cause. But what if you could travel faster than light? Special relativity predicts a strange consequence. For some observers, your journey could be seen as a journey backward in time. If you can travel backward in time, you can create paradoxes. The most famous is the grandfather paradox. You travel back in time and prevent your own grandfather from meeting your grandmother. If you succeed, you are never born. But if you were never born, you could never have gone back in time. The universe would be caught in an impossible logical loop. Any form of faster-than-light travel or communication is equivalent to a device that can send messages into the past. It would allow an effect to occur before its cause. The universe does not seem to allow for such paradoxes. The speed of light is not just a physical speed limit, it appears to be a logical one. It is the barrier that separates before from after. It is the guardian of causality. Breaking the light barrier isn't just physically difficult, it may be logically impossible because it would disrupt the coherent story of the universe. Conclusion. So, why can you never actually touch a ray of light? It is because the universe is built on a set of rules that are far more subtle than we might have imagined. You can't catch light because to do so would require infinite energy. As you chase it, your own energy of motion adds to your inertia, until you become an infinitely resistant object, frozen at the threshold. You can't catch light because the fabric of reality itself seems to prevent you. Your time would slow to a stop, and space would contract to nothingness. You would cease to exist as a being that experiences duration and dimension. And finally, you can't catch light because the universe must protect its own logical structure. The speed of light is the wall that upholds the arrow of time, preventing cause and effect from reversing into paradox. The next time you stand in a sunbeam or switch on a lamp, remember what you are witnessing. You are seeing the physical manifestation of this ultimate cosmic law. That beam of light is a ruler by which all of space and time is measured. It's not a barrier designed to frustrate us. It is the foundational promise of the universe that reality has rules, and that the world is consistent and comprehensible. You can never touch a ray of light, not because you aren't fast enough, but because the very act of trying invokes the laws that define you, that define reality, and that make your own existence possible. The limit is not a cage, it is the blueprint. The one law that prevents reality from collapsing. Let's begin with a quiet, and perhaps strange, idea. That right now, as you are sitting there, you are moving at the speed of light. There has been no launch into space. You are not journeying toward a distant star. But you are, in a very real sense, traveling at the universe's one constant speed. This isn't just a curious piece of trivia. It is a quiet rule that keeps the world from unraveling. A rule that ensures the past remains in the past, and our future arrives in an orderly, gentle way. We won't be looking at complex strings of equations. Instead, we'll explore a simple, elegant speed limit. A law so fundamental that it guides the flow of time itself, shapes the form of matter, and stands as a silent guardian against a kind of chaos that would dissolve our universe. The speed of light, as we'll see, was never really about light at all. It's about the story of cause and effect. And to understand it is to see the world in a new way. The great mystery, a universe on the brink. Before we explore that idea, let's imagine the alternative. A universe without this one, unbreakable rule. A place with no final speed limit. What would that reality look like? It would be a world where the quiet drumbeat of existence simply stops. Think of the most basic principle that gives our world its sense: cause and effect. I drop a glass, and then it shatters. A star explodes, and light years later, then we see the light. The cause always comes before the effect. It's this simple progression, this forward-moving rhythm, that allows for everything from the slow formation of galaxies to the simple act of remembering. But in a universe without that cosmic speed limit, this fundamental logic disappears. If you could send a signal, any piece of information, any object, faster than this speed, you could break the chain of causality. You could, in a way, make an effect happen before its cause. This opens the door to ideas that feel like fiction, but are deep problems for the shape of reality. The most well-known of these is the grandfather paradox. Imagine you build a machine that can send a message back in time, simply by moving faster than the speed of causality. You use it to send a simple instruction to your past self. Don't turn on the machine. Let's trace what happens. Your past self receives this message. To avoid a strange outcome, you listen. You never turn the machine on. But if you never turn the machine on, how is the message sent in the first place? The message that prevented its own sending now exists and does not exist at the same time. The cause, sending the message, is erased by its own effect. This isn't just a puzzle. It's a description of something the universe cannot seem to support, like a square circle. A universe that allows for this cannot keep a consistent history. It would be a place where events could unhappen, where the past is as uncertain as the future. The structure of time itself would dissolve into a formless soup of possibilities. Everything you know, everything that has ever happened, relies on a strict, chronological ordering of events. Without it, there is no before and after. There is no story of the universe, no evolution, no memory. There is only a nonsensical now, where everything happens at once, and nothing can ever truly become. This was the great mystery, the problem our universe needed to solve. How does it protect itself from this quiet, reality-shattering chaos? The answer, as it turns out, is not through a complicated set of rules. It is with a single, elegant, and absolute decree: a speed limit. Unpacking spacetime, the cosmic highway. To understand this speed limit, we have to picture the universe a little differently. We often think of space as a vast, empty stage where things happen. And we think of time as something separate, a clock that ticks at the same rate for everyone. Einstein's work showed us that this picture wasn't quite right. He helped us see that space and time are not separate. They are two parts of a single thing. A four-dimensional fabric called spacetime. Imagine a vast, flexible sheet. This can help us picture spacetime. Any object with mass, like a star, creates a gentle curve in this sheet. That curvature is what we feel as gravity. But this fabric isn't just a stage. It includes the three dimensions of space we know: length, width, and height, and weaves within them a fourth dimension: time. Here is the quiet and profound idea at the heart of it all. Every object in the universe, from the smallest particle to the largest galaxy, from a stone resting on the ground to you sitting in your chair, is moving through this four-dimensional spacetime at exactly the same speed. That speed is the speed of light, which we call c. You are, right now, moving at 299,792,458 meters per second. How can that be? You are sitting still. The key is to realize that this total speed is shared between the four dimensions of spacetime. You can trade your speed through space for speed through time, but your total speed through the combined fabric of spacetime is always and only c. Let's use an analogy. Imagine your journey through spacetime is like a car with its cruise control permanently set to 100 kilometers per hour. That is your total speed. Now, imagine you are on a vast, flat plain and you want to drive north. If you point the car directly north, all 100 kilometers per hour of your speed is used for moving north. But what if you turn a little and head northeast? Your total speed is still 100 kilometers per hour, but now it is split. Some of your speed moves you north, and some moves you east. You are now moving north more slowly, because some of your speed had to be used for eastward motion. If you turn to drive directly east, all 100 kilometers per hour is spent moving east, and your northward speed becomes zero. You haven't stopped, you've only changed your direction. This is almost exactly how it works in spacetime. Think of the north direction as time, and the east direction as the three dimensions of space. When you are sitting perfectly still, you are not moving through space. In this state, your entire speed, all of c*, is being used to travel through the dimension of time. This is the fastest that time can possibly move for you. Your personal clock is ticking forward at its maximum rate. Now, what happens when you stand up and begin to walk? You start moving through space. To do this, you must divert some of your fixed speed from the time dimension into the space dimensions. Just like turning the car, you are now spending some of your motion on traveling through space. And because your total speed through spacetime must stay at c*, it means your speed through time must decrease. To someone watching you from a stationary spot, your clock would begin to tick just a little bit slower. This isn't just a way of speaking. It's a physical reality. The faster you move through space, the slower you move through time. And if an object with mass could, hypothetically, ever reach the speed of light through space, it would be dedicating all of its motion to spatial travel. There would be no speed left for traveling through time. For that object, from an outside perspective, time would appear to stop. The speed of light, then, isn't just a limit for travel through space. It is a fundamental property of the geometry of spacetime. It is the fixed rate of every object's journey through the four dimensions of reality. We are all on this cosmic highway together, all moving at the same total speed. The only choice we have is in which direction we point. More toward the future in time, or more toward a destination in space. The evidence, reality bending to the rule. This idea, that time slows with motion, that we are all on a fixed speed journey through spacetime, can feel like something from a story. But it's one of the most well-tested ideas in all of science. We don't have to imagine it. We can see the traces of this rule all around us. One of the most beautiful pieces of evidence comes from tiny, fleeting particles called muons. Muons are subatomic particles, much heavier than electrons and very unstable. When they are created in laboratories, they have a very short lifespan of about 2.2 microseconds. After that, they decay into other particles. High-energy particles from outer space, called cosmic rays, are always striking Earth's upper atmosphere. When they do, they create a shower of other particles, including a stream of muons. These muons are born at high altitudes, around 10 to 15 kilometers up, and they begin falling toward the Earth's surface at nearly the speed of light, about 99.9% of c. Now, let's do some simple math. Even at almost the speed of light, a muon with a lifespan of 2.2 microseconds should only be able to travel about 660 meters before it vanishes. Because they are created many kilometers up in the atmosphere, almost none of them should ever reach the ground. But when we set up detectors, we find something astonishing. A great number of these muons do complete the journey. They survive a trip that should have been far too long for them. How is this possible? The answer is time dilation. From our perspective on the ground, as we watch these muons moving so quickly, their internal clocks are ticking much more slowly than ours. They are trading almost all of their journey through time for a journey through space. So while only 2.2 microseconds might pass for the muon, for us, much more time has gone by, enough for it to cover the distance to the ground. From the muon's own perspective, its lifespan is still just 2.2 microseconds. So how does it see itself reach the ground? This is where the other side of the idea appears. Length contraction. For the muon traveling at such high speeds, the distance from the upper atmosphere to the ground seems much shorter. The 10-kilometer journey, from its point of view, is compressed into a distance it can cross within its short life. Both viewpoints give the same result, but describe it differently. It's a perfect demonstration of Einstein's theory in motion. The laws of physics are the same for everyone, but our measurements of space and time can be different. This isn't just happening with strange particles from space. It's happening right now, high above your head, and it is essential for our modern world. The Global Positioning System, GPS, in your phone relies on a network of about 30 satellites orbiting the Earth at 20,000 kilometers high, moving at about 14,000 kilometers per hour. To find your location, your GPS receiver needs incredibly precise timing signals from at least 4 of these satellites. For the system to work, the clocks on those satellites need to be perfectly in sync with clocks on the ground. But they are not. Because of relativity, the satellite clocks run at a different rate. First, because they are moving so fast relative to us, their clocks tick slower than ours, by about 7 microseconds every day. Second, the satellites are in a place with weaker gravity. Gravity also warps spacetime, and one of its effects is that clocks tick more slowly in stronger gravity. Because the satellites are in weaker gravity, their clocks actually tick faster than ours, by about 45 microseconds per day. When you combine these two effects, the clocks on GPS satellites run ahead of ground clocks by about 38 microseconds every single day. 38 microseconds sounds like almost nothing. But in that time, light travels nearly 10 kilometers. If engineers didn't account for this relativistic effect, the entire GPS system would become useless. Positional errors would grow so quickly that after just one day, your phone might tell you you're in the next town over. The fact that GPS works is a quiet, daily proof that time flows at different rates for different observers. The engineers build the satellites with their clocks deliberately set to run a little bit slow, so that once they are in orbit, they tick at the correct rate relative to us. This isn't just a theory, it's an engineering solution built on the fundamental nature of spacetime. So if space and time are this flexible, why can't we just push a little harder and go past the speed of light? The final piece of evidence is found in the universe's energy. Einstein's famous equation, E equals mc squared, tells us that an object's energy increases with its speed. As an object gets closer and closer to C*, the energy needed to make it go even faster begins to grow enormously, approaching an infinite amount. To make any object with mass reach the exact speed of light, you would need an infinite amount of energy. To go faster, you would need more than infinite energy, which is an idea that has no meaning. The universe itself does not contain enough energy to make a single atom reach the speed of light. The speed limit is enforced by the very nature of energy and motion. So we've seen how time and space are not quite what they seem, and how a universal speed limit is woven into the fabric of reality. Welcome, sleepy scientist, to a calm exploration into the rules of the cosmos. If you're finding your perspective shifting, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share where you're watching or listening from. We break down the fundamental rules of the cosmos, and you won't want to miss where our journey takes us next. The law of causality, the guardian of reality. We have explored this idea of a trade-off in our journey through spacetime. We've seen the hard evidence left as traces in our world. Now, we can return to our first question. How does this cosmic speed limit keep reality from collapsing into paradox? The answer can be found in a concept called the light cone. It's a simple, but powerful, way to picture causality in spacetime. Imagine an event. It could be you snapping your fingers or a distant star going supernova. This event happens at a specific point in space and a specific moment in time. From this event, imagine light expanding outwards in all directions, forming a growing sphere. If we were to draw this, with time moving upwards, this expanding sphere of light would trace out a cone. This is the asterisk future light cone. This cone contains all the points in spacetime that can ever be affected by your original event. For something to be influenced by the snap of your fingers, it has to be somewhere that the sound or light from that snap can reach. Since nothing can travel faster than light, nothing can ever leave this cone. Any event outside the future light cone is causally disconnected. The information simply has not had time to get there. In the same way, we can trace back in time. The asterisk past light cone asterisk is another cone, pointing downwards. It represents all the events in the past that could have possibly influenced the snap of your fingers. Your entire existence is a sequence of these events, connected by light cones. Your birth is an event. Everything you have ever experienced lies within the future light cone of your birth. Everything that could have led to your existence lies within its past light cone. This structure is the structure of causality. It is the geometric shape of before and after. Now, we can see why traveling faster than light would shatter this structure. If you could send a signal faster than light, you would be sending a message to a point outside the future light cone. You would be creating a link between 2 points that are supposed to be disconnected from each other. Here, things become quietly strange. One of the core ideas of relativity is that there is no absolute now for everyone in the universe. The order of events can seem different to different people moving relative to each other. For events that are inside each other's light cones, everyone will agree on the order. Everyone agrees the glass was dropped before it shattered. But for events outside each other's light cones, observers can disagree. Some might see event A happen before event B, others might see B happen before A. This usually doesn't matter, because those events can't affect each other anyway. However, if you create a faster than light link, you create a cause and effect relationship between events in this ambiguous zone. Let's go back to our machine. 1. At 12 p.m., you send a faster than light message to a spaceship. 2. Now, imagine another observer flies past you at very high speed. Because of how relativity works, their view of spacetime is slightly tilted compared to yours. 3. From their perspective, they could see the message arrive at the spaceship before you even sent it. For them, the effect happens before the cause. This is strange, but it is not yet a paradox. The paradox appears when the spaceship sends a message back to you. They could send a reply that, from your perspective, also seems to travel back in time, arriving at your location before you sent the original message. This brings us right back to the grandfather paradox. You could get a reply to a message you haven't sent yet. You could get a message from the future telling you not to send the first one. If you obey, the entire chain of events unravels. The speed of light prevents this from ever happening. By being the absolute limit for any interaction, it ensures that cause and effect stay neatly inside their light cones. It guarantees that no matter how someone is moving, the order of cause and effect remains unbreakable. So, the speed of light is not a frustrating barrier preventing us from exploring the stars. It is the supreme law that preserves the logical story of the universe. It is the guardian of causality, the enforcer of the arrow of time. Without it, the past, present, and future would bleed together, and the ordered, predictable world we live in would be impossible. Cosmic implications. A universe built on limits. This role of C as a guardian extends from the subatomic to the truly cosmic. It shapes our entire universe, sometimes in ways that seem to defy the rule itself. A common point of confusion comes when we look at the expansion of the universe. We see distant galaxies, and the farther away they are, the faster they appear to be moving away from us. There is a point, a cosmic horizon, beyond which galaxies are receding from us faster than the speed of light. Doesn't this break the ultimate speed limit? The answer is no, and it shows us an important difference. The speed limit of c applies to the motion of objects through space. Those distant galaxies are not flying through space away from us like rockets. Instead, the fabric of spacetime itself is expanding, carrying the galaxies with it. The raisin bread analogy is perfect for this. Imagine a loaf of raisin bread dough. The raisins are galaxies, and the dough is spacetime. As the dough expands, all the raisins move farther apart. A raisin on one side of the loaf might see a raisin on the far side moving away very quickly. But the raisins themselves are not moving through the dough. They are still, while the dough between them stretches. This is what happens in our universe. For galaxies that are very far away, the cumulative expansion of all the space between us adds up to a recession speed greater than c. Locally, however, in their own patch of spacetime, nothing is breaking the speed limit. No information is being sent from one of those galaxies to another faster than light. Local causality is never violated. The rule holds. This speed limit also determines the size of our observable universe. The universe is about 13.8 billion years old. You might think that means we can only see things that are 13.8 billion light-years away. But because space itself has been expanding, the most distant objects whose light is only now reaching us are currently about 46 billion light-years away. That boundary, the edge of what we can see, is a direct result of the finite speed of light. It defines our cosmic horizon, the bubble of information we are connected to. But why this particular speed? Why is c about 300,000 kilometers per second? The number itself is just an accident of our human units, the meter and the second. In a more natural system of units, the speed of light would simply be 1. It is the fundamental speed against which all other speeds are measured. What matters is not the number, but that it is always constant. This has been tested with incredible precision. Recent experiments, like those at the Large High-Altitude Airshower Observatory, LHAASO, have provided some of the most stringent tests. In recent years, LHAASO detected a gamma-ray burst from billions of light-years away, containing particles of light, photons, with a vast range of energies. Some ideas about the universe suggested that very high-energy photons might travel at a slightly different speed than low-energy ones. Over a journey of billions of light-years, even a tiny difference in speed should have been noticeable. LHAASO found no such difference. All the photons arrived at the same time, confirming the speed of light is constant to an unprecedented degree. These results quietly reinforce c as a true, unshakable constant of nature. This brings us to a final, more philosophical thought. We sometimes see limits as restrictive. But in physics, and perhaps in life, limits are what create structure and meaning. A game without rules is not a game, just noise. A language without grammar is not a language, just babble. A universe without the limit of c would be formless chaos. Without a finite speed for interactions, there could be no stable atoms. There could be no predictable chemistry, no formation of stars and planets, no evolution of life. The very existence of before and after, the sequence that allows for complexity to grow over time, is a direct result of this one, universal limit. The speed of light is the primary rule. It is the constraint that gives the universe its form, its structure, and its ability to create anything at all. Conclusion. So we find ourselves back where we started. You are moving at the speed of light. Not through space, but through the four-dimensional fabric of spacetime. Every second, you traveled 299,792,458 meters into your own future. This journey is guided by one unbreakable law. A law that is not really about light, but about the speed of causality itself. It is the universe's quiet solution to the problem of paradox, its way of ensuring that reality remains a coherent, logical story. This single rule guides the flow of time, provides the structure for matter, and draws the boundaries of our cosmos. It isn't a cosmic prison, keeping us from the stars. It is the foundational principle that makes stars, planets, and our own existence possible in the first place. It is the law that prevents reality from collapsing, and in doing so, allows a story, the story of our universe, to unfold, one ordered moment at a time. Every step you take is you navigating your own path through this four-dimensional reality, trading moments of time for movement in space. The law doesn't stop your journey. It is the very thing that makes it possible. What are your thoughts on this quiet, fundamental rule of the cosmos? Feel free to share them in the comments below. And for more journeys to the edge of our understanding, make sure you're subscribed. What your body would see at 99% light speed. What if you could take a trip where, for every single minute that passes for you, an entire century flies by back on Earth? It sounds like the start of a sci-fi movie, but it's a real prediction from Albert Einstein's theory of relativity. It's what happens when you get close to the universe's ultimate speed limit, a cosmic boundary that rules everything from the tiniest particles to the largest galaxies. A speed so absolute that reality itself begins to warp, bend, and twist as you approach it. We've all wondered what that would be like. What if we could build a ship that could actually travel at 99% of the speed of light? What would you, as the passenger, really see and feel? We're not just talking about watching stars streak by. We're talking about fundamental changes to your perception of space, of time, and of the light that lets you see anything in the first place. This is a journey to the very edge of what's possible. A place where time slows to a crawl, distances shrink, and the energy needed to go just a little bit faster spirals toward infinity. It's a trip that would sever your connection to the rest of human history, turning you into a time traveler hurtling toward a future you can't possibly imagine. Let's chase a beam of light and unravel what your body, your senses, and your clock would actually witness at the dizzying speed of 99% of the speed of light. Picture this. You're in the cockpit of a spaceship, and you are accelerating hard. The hum of the engines is a constant roar as you push deeper into space. On your screen, a number climbs. 80% of light speed, 90%, 95%. Until you finally settle in at 99.9% of the cosmic speed limit. You look out the viewport, and the universe is no longer familiar. The stars in front of you have squeezed into a single, brilliant point of white-hot light, while everything behind you has dissolved into a perfect, inky blackness. Your ship, 100 meters long to you, would look to an outside observer like a flattened disk just a few meters across. And the craziest part? While you spend a calm, quiet minute checking your instruments, a full 100 years of human history has just unfolded back on Earth. This isn't science fiction, it's physics, and it's the bizarre reality that awaits anyone who gets close to the universe's ultimate speed limit. So what is really happening here, and what would you see on this incredible journey? The cosmic speed limit and the beginning of the journey. Before we can really get into the weirdness of our 99% light speed trip, we need to understand why it's so weird to begin with. The universe has a fundamental, unbreakable rule. There is a cosmic speed limit. That speed is the speed of light in a vacuum, a constant called c, which is precisely 299,792,458 meters per second. Nothing with mass can ever reach this speed, and anything without mass, like a photon of light, must travel at this speed. This isn't just a technological hurdle we can eventually overcome, like the sound barrier. It's a fundamental property of spacetime itself. Einstein's theory of special relativity is built on two simple, yet world-altering, ideas. First, the laws of physics are the same for everyone moving at a constant speed. Second, the speed of light in a vacuum is the same for all observers, no matter how fast they're moving. That second point is what really breaks our brains. Imagine you're driving down the highway at 100 kilometers per hour and you turn on your headlights. You might think someone on the side of the road would see that light traveling at the speed of light plus your 100 kilometers per hour, but they don't. They see it traveling at exactly c. You, in the car, also see the light moving away from you at c. It is constant and absolute, and this bizarre, unshakable fact is where all the weirdness of high-speed travel comes from. Now, let's get back on our ship. You start your journey from Earth. The engines fire up, and you feel a powerful but steady acceleration. At first, things feel pretty normal. You're moving incredibly fast, but your day-to-day life inside the ship hasn't changed. At 10% of the speed of light, about 30,000 kilometers per second, the effects of relativity are still tiny. You could travel for years and the time difference compared to Earth would be barely noticeable. At these, slower, relativistic speeds, the universe still looks and feels mostly like the one you left behind. But our goal is 99% of light speed, and the trip from 10% to 99% is where reality starts to come apart at the seams. As your ship keeps accelerating, you pour more and more energy into the engines. You push and push, but your speed doesn't increase in a straight line. The closer you get to the speed of light, the more the universe stubbornly resists your efforts. Going from a standstill to 99% of light speed is one thing. But as we'll find out, the energy needed to get from 99% to 99.9% is more than all the energy you've spent so far. This is your first clue that you are approaching a very special kind of boundary. Inside your ship, you feel fine. You can walk around, pour coffee, watch a movie. From your perspective, you're stationary, and the universe is rushing past you. This is a key part of relativity. There's no such thing as being at rest, in an absolute sense. Your own frame of reference always feels normal. The view out your window, however, is starting to tell a very different story. The universe is no longer the familiar, static web of stars you once knew. It's becoming a dynamic, distorted, and deeply alien landscape. Your journey into the bizarre has begun. What your body would see, the warping of vision. As you push past 90% and on toward 99% of the speed of light, the first and most dramatic changes are visual. What you see out the viewport isn't just stars streaking by like in the movies. The reality is far stranger, governed by two phenomena: the relativistic Doppler effect and the aberration of light. Let's start with color. You already know the Doppler effect from sound. An ambulance siren sounds high-pitched as it approaches and low-pitched as it drives away. Light does something similar, but with color. The frequency of a light wave determines its color. Higher frequencies shift light toward the blue end of the spectrum, called blue shift. Lower frequencies shift it toward the red end, known as redshift. As you rocket forward at 99% light speed, the light from stars in your direction of travel gets massively compressed. Their light waves hit your ship with a much higher frequency. Visible light from a star would be blue shifted right past violet and into the ultraviolet, X-ray, and even gamma-ray parts of the spectrum. You'd need special sensors just to see it. At the same time, the light from stars behind you gets stretched out. Their visible light is redshifted down into low-energy infrared, microwaves, and radio waves, making them totally invisible to your eyes. The second effect, aberration, changes the apparent position of the stars. Think about standing in the rain. If the rain is falling straight down but you start running, it seems to come at you from an angle. The faster you run, the more it seems to come from the front. The same thing happens with starlight. As your speed increases, the light from stars all around you, to your sides, even from slightly behind, appears to shift and crowd into the direction you're heading. Combine these two effects at 99% the speed of light, and the view is incredible. The entire sky warps. All the stars in the universe appear to bunch up into a small, concentrated tunnel of light directly in front of you. This tunnel would be dazzlingly bright, but the light inside it would be so heavily blue shifted that it would look like a single, searingly bright, featureless disk of white or bluish-white light. A starbow, as some have called it. And the rest of the sky? Behind you and to your sides, there would be nothing. Absolute blackness. The light from those stars is still there, but it's been so redshifted into radio waves that it's completely invisible to you. You'd be flying through a black void with a single, terrifyingly bright jewel set directly ahead. There's one more strange optical illusion, the Terrell rotation. For a long time, physicists assumed that objects you flew past would look squashed flat because of an effect called length contraction. But it turns out, that's not what you'd actually see. Because the light from different parts of a nearby object reaches your eyes at slightly different times, the object would actually appear rotated, not flattened. So, if you flew past a spherical planet, it wouldn't look like a pancake. In a bizarre twist of relativistic optics, it would still look like a sphere, as if it had simply been turned in space. So, what you see is a universe transformed. Color is distorted beyond recognition. The entire cosmos is squeezed into a forward-facing tunnel of blinding light, and the space behind you is a perfect, empty black. It's a vision so alien it shows just how far you've come from home. The distortion of time, the experience of dilation. While your view of space is warping, something even weirder is happening to time itself. Inside the ship, everything feels normal. Your heart beats at its usual pace, a minute feels like a minute, and your clocks tick away normally. But this personal experience is deeply deceiving. Compared to Earth, your time is slowing to a crawl. This is the famous phenomenon of time dilation. At 99% of the speed of light, the Lorentz factor, the number that governs these relativistic effects, is about 7. This means for every 7 years that pass on Earth, only 1 year passes for you. If you push your speed to 99.9%, that factor jumps to around 22. At 99.999%, it's over 223. A single year on your journey would mean more than 2 centuries had passed on Earth. To understand why this happens, think of a light clock. Imagine a clock that bounces a photon of light between 2 mirrors. If the mirrors are 300,000 kilometers apart, it takes the photon 1 second to go from one mirror to the other. Tick, 1 second. Talk, 2 seconds. Now, put that clock on your spaceship and let's watch it from Earth as you fly by. From your perspective on the ship, the photon is just going straight up and down. Tick, tock, normal. But from our view on Earth, we see the clock moving sideways. For the photon to get from the bottom mirror to the top one, it now has to travel on a diagonal path, because the top mirror has moved forward. A diagonal path is longer. And since the speed of light is constant for everyone, a longer path means it takes more time. So, from Earth, we see your clock ticking slower than ours. This isn't an illusion, it affects everything. Your heartbeat, your metabolism, the signals in your brain. They all slow down by the same factor. You don't feel any different because your own perception of time slows down right along with everything else. You only see the difference when you compare your clock to one back on Earth. This isn't just a theory, we use it every day with GPS satellites. They orbit the Earth at about 14,000 kilometers per hour. Because of that speed, special relativity dictates that their clocks should run slower than ours by about 7 microseconds every day. But that's not the whole picture. Einstein's general relativity adds another twist. Gravity also warps time. Because the satellites are in a weaker gravitational field than we are on the surface, their clocks actually tick faster by about 45 microseconds a day. The faster effect from weaker gravity wins out, so the satellite clocks get ahead of ground clocks by about 38 microseconds daily. If engineers didn't constantly correct for this, GPS navigation would be off by over 11 kilometers every single day, making it useless. An even cooler proof comes from the sky. Cosmic rays hit our upper atmosphere and create a shower of unstable particles called muons. Muons have an incredibly short lifespan, about 2.2 microseconds. Even traveling near the speed of light, they should only be able to travel about 660 meters before most of them decay. This means we shouldn't detect very many of them down here at sea level, thousands of meters below where they're made. And yet, we detect them all the time. Why? From our perspective, the muon's internal clock is ticking incredibly slowly because of time dilation. Their 2.2 microsecond lifespan gets stretched out, allowing them to survive the long trip down to the surface. For you, our traveler, this means you are becoming a time traveler. You're trading your place in the present for a one-way ticket to Earth's future. A 5-year round-trip journey to a nearby star at 99% light speed might feel like 5 years to you, but when you returned, you'd find that 35 years had passed on Earth. Your friends would be decades older, society would have changed, and you would be a visitor from the past. This journey is already bending our minds around time and space. But we're about to hit the biggest wall of all, the wall of infinity. If exploring the fundamental rules of the universe gets you excited, make sure you subscribe and hit the notification bell. We break down the biggest questions in physics every week, and you won't want to miss what's coming up next. The compression of space, the experience of contraction. As time stretches, space does the opposite, it shrinks. This is the third major effect of special relativity you'd experience: length contraction. And just like time dilation, this isn't an illusion. From the perspective of someone on Earth watching you, the very fabric of space in your direction of motion appears to compress. At 99% of the speed of light, where the Lorentz factor is about 7, your 100-meter-long spaceship would appear to an observer on Earth to be only about 14 meters long. It would look squashed, but only in the direction of travel. Its height and width would look normal. But remember, from your point of view, you're the one who is stationary. You measure your ship, and it's still 100 meters long. For you, it's the rest of the universe that's moving at 99% of the speed of light. So, from your perspective, it is the universe itself that is contracting. This has a huge impact on your journey. Let's say you're flying to Alpha Centauri, our nearest star system, about 4.3 light-years away. From Earth's perspective, even at 99% of c, that trip should take a bit more than 4.3 years. But from your perspective on the ship, the distance to Alpha Centauri has shrunk. The 4.3 light-years of space between Earth and the star system has contracted by that same factor of 7. To you, the journey is only about 0.6 light-years long. Traveling at 0.99 c, this shrunken distance takes you only about 0.6 years, or roughly 7 months, to cross. This is the beautiful symmetry of relativity. The observer on Earth explains how you made the journey so quickly by saying your time slowed down. You explain it by saying the distance got shorter. Both of you are correct in your own frame of reference. They're just two different ways of describing the same event. This also resolves a potential paradox. How can you travel 4.3 light-years in just 7 months without breaking the speed of light? The answer is that from your point of view, you didn't travel 4.3 light-years. You traveled a much shorter distance. The speed of light is still the ultimate limit in every frame of reference. The muon experiment proves this, too. We on Earth see the muon's life extended by time dilation. But from the muon's perspective, its lifespan is just the normal 2.2 microseconds. The reason it reaches the ground is because, to the muon, the distance from the upper atmosphere to sea level is drastically contracted. A journey that is kilometers long in our frame becomes just a few hundred meters in its frame, a distance it can easily cross. Time dilation and length contraction are two sides of the same coin. For you, the astronaut, this makes interstellar travel seem much more possible. The faster you go, the shorter the universe becomes. If you could reach 99.99% of light speed, the 2.5 million light-year distance to the Andromeda Galaxy would shrink to just over 35,000 light-years from your perspective. It's still a long trip, but not millions of years. Of course, when you got there, you'd find that 2.5 million years had indeed passed back home. Space contracts to make the journey possible, but time dilates to make you pay the price. The wall of infinity, the problem of energy. So, we've been talking about what happens at 99% of the speed of light. Why not just push a little harder and hit 100%? Why can't we just reach the speed of light? The answer is the most intimidating barrier in all of physics, the wall of infinite energy. In old-school Newtonian physics, kinetic energy is simple: half the mass times the velocity squared. In that world, if you keep applying a force, your speed just keeps going up and up, with no theoretical limit. But we know the universe doesn't work that way. Einstein's special relativity gives us a new equation for kinetic energy. The key part involves that Lorentz factor, gamma. At low speeds, this equation works almost exactly like the old Newtonian one. But as your velocity gets closer to the speed of light, gamma skyrockets towards infinity. Your kinetic energy is tied directly to this factor, so as you approach light speed, the energy you need to go faster explodes. Let's put some numbers on it. Accelerating one person to 10% of light speed requires a mind-boggling amount of energy, roughly 300 times the energy released by the Hiroshima bomb. And that's just to get started. To go from 90% to 99% of light speed requires more energy than all the previous steps combined. To go from 99% to 99.9% requires even more. The energy cost for each extra 9 you add after the decimal point gets exponentially bigger. You're pouring in colossal amounts of energy for smaller and smaller gains in speed. To actually reach your velocity would equal the speed of light, gamma would become infinite, and the kinetic energy required would be infinite. You would need an infinite amount of energy to accelerate any object with mass to the speed of light. Since there isn't an infinite amount of energy in the universe, it's impossible. We see this in our most powerful machines, particle accelerators. At CERN's Large Hadron Collider, protons are accelerated to 99.9999991% of the speed of light, just 3 meters per second slower than light itself. To do this, CERN uses enough electricity to power a small city. But if they wanted to add another 9 to that speed, the energy cost would be astronomical. The LHC proves the principle perfectly. The closer you get to the more insane the energy cost becomes. For years, people explained this using the idea of relativistic mass, that an object's mass increases as it speeds up. While it can be a simple way to think about it, most physicists now consider that idea outdated. Your intrinsic mass doesn't change. What changes is spacetime itself, which demands ever-increasing amounts of kinetic energy to go faster. It's not that your mass becomes infinite, it's that the energy required to speed up your unchanging mass becomes infinite. The cosmic speed limit isn't a suggestion, it's an absolute law, enforced by the very structure of energy and spacetime. The return and the paradox. Let's finish our trip. You've spent a year at 99.9% of light speed exploring a distant star. For you, it was a year. You aged a year, used a year's worth of supplies, and remember a year of events. Now you turn around and head back to Earth, another 1-year journey. You arrive back home after your 2-year round trip. But the Earth you find isn't the one you left. At 99.9% light speed, the Lorentz factor is about 22. For your 2 years of travel, roughly 44 years have passed on Earth. You step out of your ship, but the friends you left behind are now decades older or gone. The world has moved on. New technologies, new cultures, new history. You are a relic, a person from the past dropped into the future. This scenario is known as the twin paradox. It asks, if all motion is relative, why does only the traveling twin age less? From the astronaut's perspective, wasn't it the Earth that was moving away? Shouldn't the twin on Earth be younger? The paradox is solved when you realize the twin situations weren't the same. The twin on Earth stays in one consistent frame of reference. The traveling twin doesn't. You have to accelerate to leave, decelerate to stop, accelerate to come home, and decelerate to land. It's this acceleration, the changing of reference frames, that breaks the symmetry. The act of turning around is what makes you the one who experiences less time. While you were cruising, you both saw each other's clocks running slow, but the acceleration you went through makes the time difference real and measurable when you're finally back together. So you return not just as a space traveler, but as a time traveler. The same laws of physics that let you cross vast distances by shrinking space also forced you across vast gulfs of time by stretching it. You've seen what happens at the edge of the ultimate speed, and the price is your connection to your own time. Conclusion: a journey to 99% of the speed of light is a journey into a universe that is fundamentally alien to us. It's a place where your vision warps into a tunnel of fierce, blue-shifted light and an abyss of red-shifted darkness. A place where space itself compresses to shorten your trip, but only by stretching time to an unrecognizable degree. We've learned that time and space aren't the fixed, rigid background we think they are. They are a dynamic, interwoven fabric, spacetime, that bends and distorts with motion. We've seen that the universe's speed limit, c, isn't just a barrier, but a fundamental constant that dictates the relationship between energy and mass, a fact proven every day by our GPS systems and the fleeting lives of cosmic muons. And finally, we've confronted the wall of infinity. The reason you can never reach the speed of light is that it would require an infinite amount of energy, a lesson we learn from giant particle accelerators like the LHC. This cosmic speed limit defines the boundary between the possible and the impossible. So, while traveling at 99% of light speed would give you a glimpse of the universe's deepest secrets, it would also disconnect you forever from the world you knew. It's a powerful reminder that the laws of physics are both wondrous and unforgiving, painting a picture of reality far stranger and more magnificent than we could ever imagine from our quiet corner of the cosmos. The speed limit where time stops forever. Imagine sprinting so fast that your watch just stops. Not because it's broken, but because for you, time itself has slammed on the brakes. Now, imagine you're still accelerating, pushing toward the fastest speed the universe allows. This isn't a sci-fi paradox. It's a real description of what happens at the edge of reality. There's a speed limit in our universe. But it's not really about how fast you can go. It's about how much you're willing to give up. What if I told you there's a speed so extreme that your journey across the entire galaxy would feel like it took no time at all? That you'd arrive at the exact same moment you left? This isn't a wild theory. It's a fundamental rule of our universe, hardwired into the fabric of space and time. So, why does this ultimate speed limit exist? And why does time seem to shatter when you reach it? To answer that, we have to forget everything we think we know about how to move. The intuitive lie of speed. Our entire lives are built on a simple, intuitive idea about speed. And it's completely wrong. It feels like basic math. If you're on a bus going 50 kilometers per hour, and you walk to the front at 5 kilometers per hour, your friend on the sidewalk sees you moving at 55. Your speed and the bus's speed just add up. It's common sense, right? It's called Galilean relativity, and for the slow-moving world we live in, it works just fine. If you're on a train zipping along at 100 kilometers per hour and you throw a baseball forward at 80, anyone on the platform sees that ball fly by at 180. Simple. Obvious. We've built our world on this rule, launching rockets and driving cars assuming velocities just add together. It feels as solid as the ground under our feet. But what if I told you this common sense rule is just a local suggestion? An approximation that only works because we are all moving at a crawl compared to the true cosmic speed limit. When you start to really push it, when you accelerate to a real fraction of that ultimate speed, this simple addition falls apart. The universe, it turns out, plays by a much stranger set of rules. Let's go back to that train. It's moving at, say, half the speed of light. But this time, instead of throwing a baseball, you turn on a flashlight and point it forward. The light beams out. You, on the train, measure its speed. It's the speed of light. No surprise there. But what does your friend on the platform see? Our everyday logic says they should see the speed of the train plus the speed of light. But they don't. They measure the speed of that light beam and get the asterisk exact same number you did. How is that possible? How can two observers, moving at wildly different speeds, measure the exact same velocity for something else? It's a paradox that broke physics for decades. The universe has to be fudging the numbers somewhere else to make this work. And to find out where, we have to talk about the most stubborn thing in all of creation. The stubbornness of light. The journey to this cosmic speed limit starts with a puzzle. In the late 19th century, physicists were fascinated by a new set of equations from James Clerk Maxwell. They perfectly described electricity and magnetism, and they made a wild prediction. That light is an electromagnetic wave that travels at a very specific speed. About 299,792 kilometers per second in a vacuum. We call it C. But this created a huge problem. A speed relative to asterisk what? Every other wave we knew needed a medium. Sound needs air. Ripples need water. So, physicists figured there must be some invisible substance filling all of space, the luminiferous ether. Light, they assumed, was a vibration in this ether, and C was its speed relative to it. This made sense, and it led to a testable idea. The Earth is moving through space, so it must be moving through the ether. This should create an ether wind, like the wind you feel on a bike. If you measure the speed of light going with the wind, it should be faster than when you measure it going against the wind. In 1887, Albert Michelson and Edward Morley set out to detect this wind. They built an incredibly sensitive device that split a beam of light, sent the two halves on different paths, and then brought them back together. Any difference in speed would create a distinct pattern. They rotated it. They waited for different seasons. They tried everything to catch this wind. The result? Nothing. Absolutely nothing. There was no wind. The speed of light was stubbornly, maddeningly, impossibly the same, no matter how they measured it. This is probably the most famous failed experiment in history, and it drove scientists crazy. It took a young, unknown patent clerk named Albert Einstein to make the truly radical leap. In 1905, he didn't try to explain away the constant speed of light. He built his entire reality on top of it. He started with two simple rules. First, the laws of physics are the same for everyone who isn't accelerating. Second, the speed of light in a vacuum, C, is the same for all observers, no matter how they're moving. Think about what that means. You're on a spaceship hurtling forward at half the speed of light. You turn on your headlights. You measure the light leaving your ship at speed C. Your friend, standing still on a space station as you fly past, also measures the light from your headlights moving at speed C. Not C plus half C. Just see . This is the central mystery. If speed doesn't add up anymore, something else must be changing to make the universe's books balance. If the speed of light is absolute, then our measurements of space and time must be flexible. And Einstein showed that's exactly what happens. The currency of spacetime, the core reveal. To solve the puzzle of light, we have to completely rethink space and time. We think of them as separate. Space is the 3D stage, length, width, height. Time is the universal clock ticking in the background, the same for everyone. That was Newton's view. It's our view. And it's wrong. Hermann Minkowski, one of Einstein's old professors, realized what this all meant. He declared, henceforth, space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. He gave us the idea of a single, four-dimensional fabric, spacetime. Now, here is the single most important idea in all of this. Get ready. Every single object in the universe, you, me, this planet, everything, is moving through spacetime at one, single, constant speed. The speed of light, asterisk. You are moving at the speed of light right now. So is the chair you're sitting on. How can that be? You're sitting still. This is where we need a new analogy. Your asterisk spacetime budget. Imagine your total motion through spacetime as a fixed budget of speed, always equal to see . You can choose how to spend this budget. You can spend it moving through the three dimensions of space, what we just call speed, or you can spend it moving through the one dimension of time. The more you spend on moving through space, the less you have to spend on moving through time. Let's break it down. When you're sitting perfectly still, your speed through space is 0. At that moment, you are spending your entire space-time budget traveling through the time dimension. You are moving into the future at the maximum possible rate. Your watch is ticking, you're aging. This is time passing as fast as the universe allows. Now, stand up and walk across the room. You've just reallocated a tiny fraction of your speed budget. You've diverted it away from moving through time and into moving through space. To keep your total speed through spacetime constant at see . The universe demands a trade-off. Your speed through the time dimension has to decrease. For you, time itself is now passing just a tiny bit slower than it was for the you who was sitting still. This isn't a metaphor, it's a geometric fact. We can even draw it. Imagine a graph where the vertical line is your speed through time and the horizontal line is your speed through space. Your total motion is the hypotenuse of a right triangle, and its length is always see . If you're at rest, the horizontal line, space speed, is 0. So the vertical line, time speed, must be equal to see . But as you start to move through space, that horizontal line gets longer. Since the hypotenuse has to stay the same length, the vertical line, your speed through time, must get shorter. You are trading motion through time for motion through space. This is the secret behind time dilation. Time slows down for a moving object because that object is using some of its universal motion for space, leaving less for time. You can't go faster than see . Through space for the same reason you can't spend more money than you have. To move at see . Through space would mean spending your entire budget on it, leaving nothing left for moving through time. And that's where things get really weird. The light clock, visualizing the trade-off. This idea of a spacetime budget can feel a little abstract. So let's make it visible with a brilliant thought experiment. The asterisk light clock. It's the simplest clock imaginable. Two mirrors facing each other, with a single photon of light bouncing between them. Every time the photon hits a mirror, that's one tick. The distance between the mirrors is fixed, and the photon's speed is always see . It's a perfectly steady clock. Now, let's put you and one of these clocks on a stationary platform. You watch your clock. The photon bounces straight up and down. Tick, tock, Tick, tock. Perfect. Next, we put an identical clock on a transparent spaceship and send it flying past you at, say, 80% of the speed of light. You watch this moving clock through a telescope. What do you see? From your perspective, the clock is moving sideways. So when the photon leaves the bottom mirror, the top mirror moves to the right before the photon can get there. To catch up, the photon has to travel a longer, diagonal path. It has to do the same thing on the way back down. For every single tick of the moving clock, you see its photon traveling a much greater distance than the photon in your clock. And here's the kicker. The universe's one unbreakable rule is that the speed of light is constant. You must measure the speed of the photon in the moving clock to be exactly the same as the one in your clock. So, if the moving photon travels a longer distance but at the exact same speed then its journey must take more time. From your platform, you literally watch the spaceship's clock ticking slower than your own. There's nothing wrong with the moving clock. For the astronaut on board, their photon is just going straight up and down. Their clock is fine. It is time itself that is flowing at a different rate for them relative to you. The light clock makes the spacetime budget visible. The photon's total speed, gets split. Part of it is used for the horizontal motion of the spaceship. That leaves less speed available for the vertical, timekeeping journey between the mirrors. Its vertical speed goes down, so the clock ticks slower. It's a direct demonstration that moving through space costs you speed through time. Escalating to the edge, time dilation isn't an on-off switch, it's a sliding scale. And as you get closer to the speed of light, the effect gets insane. Let's take a trip. At everyday speeds, the effect is basically zero. You're trading a rounding error from your time budget. But let's get on a spaceship. You accelerate to *50% of the speed of light. Things start getting weird. For every 100 seconds that pass for your friend back on Earth, only about 87 seconds pass for you. Time is flowing 13% slower for you. Push it to *86.6% of the speed of light. At this speed, the math is beautiful. Your time is now passing at exactly half the rate as on Earth. For every 2 years your friend ages, you age only 1. Now things escalate quickly. You push the engines to *99% of the speed of light. For every year you experience, more than 7 years pass on Earth. *99.9% of the speed of light. Your time slows by a factor of nearly 22. A single year on your ship is more than 2 decades on Earth. How about *99.9999% of the speed of light? You could fly to the nearest star system, Proxima Centauri, and back. A trip that takes over 8 years from Earth's perspective. For you, the whole round trip would last just a few days. At *99.9999999% of the speed of light you could cross the entire Milky Way galaxy, 100,000 light years, in what would feel to you like just 1.4 years. But when you got back, 200,000 years would have passed on Earth. So why not just push it that last tiny bit to 100%? The answer is energy. This is where Einstein's famous equation, E=mc², comes in. The full version for a moving object shows that as your velocity approaches the energy needed to accelerate you approaches infinity. To get from 99% to 99.9% light speed takes a colossal amount of energy. To go from 99.999% to exactly 100% would require an infinite amount of energy. You would need all the energy in the universe. The universe demands a price for speed, and the price for that final fraction of a percent is literally everything. The speed of light is a horizon you can approach forever, but never touch. If your view of the universe is starting to feel a little wobbly right now, take a second to hit that subscribe button. We break down the biggest ideas in physics every single week, and you don't want to miss where we're going next. Arrival at forever. What happens at light speed? We've established that if you have mass, you can't reach the speed of light. It's a mountain you can never summit. But we know what the summit looks like, because some things live there permanently. Particles of light themselves, photons. Photons are massless, so the infinite energy rule doesn't apply to them. In fact, for a massless particle, traveling at (c) isn't optional, it's mandatory. So, what is reality like from a photon's point of view? Let's go back to our spacetime budget. You trade speed through time for speed through space. A photon moves through space at the speed of light. It is spending 100% of its spacetime budget on moving from A to B. So, what's left for moving through time? Zero. Nothing. If your speed through space is (c), your speed through time must be zero. For a photon, time does not pass. At all. A photon is emitted from a quasar 13 billion light-years away. For 13 billion years, from our perspective, it travels across the universe. Finally, it ends its journey by hitting a cell in your eye. For us, eons have passed. From the photon's perspective, its creation and its destruction, its emission from that quasar and its arrival in your eye, happen at the exact same moment. It experiences no journey. It experiences no time. For the photon, the entire 13 billion year odyssey is instantaneous. This is the ultimate destination. The speed of light isn't a barrier. It's a state of being where the journey through time comes to a complete halt. You don't break the rules, you just enter a place of timelessness, a forever now. The finish line isn't a wall, but an existence where past, present, and future merge into a single point. Proof in the real world. Okay, this all sounds like trippy philosophy. But it's not a theoretical game. These effects are real, measurable, and you rely on them every day. One of the coolest proofs comes from tiny particles called muons. Muons are created when cosmic rays slam into the upper atmosphere, about 10 kilometers above our heads. They're super unstable, with a lifetime of just 2.2 millionths of a second. Now, let's do the simple math. These muons travel at about 99.9% of light speed. Even so, in 2.2 microseconds, they should only be able to travel about 660 meters before they decay. Since they're created 10 kilometers up, none of them should ever reach the surface. And yet, we detect them down here all the time. How do they survive the trip? Time dilation. From our perspective, because the muons are moving so fast, their internal clocks are ticking much slower than ours. Their 2.2 microsecond lifespan gets stretched out, giving them more than enough time to reach the ground. From the muon's perspective, its clock is ticking normally. So how does it explain reaching the ground? From its point of view, the atmosphere is rushing up at it so fast that the 10-kilometer distance is drastically shortened. Both perspectives agree on the outcome. The muon makes it. But the proof you use every single day is your phone's GPS. The GPS network is a swarm of satellites, each with a hyper-accurate atomic clock. Your phone gets signals from several satellites and uses tiny differences in their timing to figure out where you are. For this to work, the satellite clocks and ground clocks must be perfectly synced. But relativity says they can't be. The satellites are moving at 14,000 kilometers per hour. So special relativity says their clocks should tick slower than ours, by about 7 microseconds a day. But they're also in weaker gravity, where general relativity says clocks tick faster, by about 45 microseconds a day. The net result is that GPS clocks should get ahead of Earth clocks by 38 microseconds every day. That may sound tiny, but it would cause a position error that grows by 10 kilometers every single day. Your GPS would be useless. The engineers who built the system knew this. So they built relativity into it. The satellite clocks are designed to tick at a slightly different rate to perfectly cancel out the effects of relativity. The fact that your phone can find the nearest coffee shop is daily, practical proof that time runs differently depending on your speed and gravity. Conclusion. So, we come back to the ultimate speed limit. It isn't a wall at the end of a racetrack. It's the governing constant of our universe, the central pillar that space and time must bend around. The single idea to hold onto is this: we are always, moving through space-time at the speed of light. Our only choice is not if we travel at this speed, but in which direction. Every moment you sit still, you are firing your entire motion along the axis of time, hurtling into your future at the fastest rate possible. When you get up and move, you trade a little bit of that journey through time for a journey through space. This is why the speed of light is the limit. It represents a full commitment, diverting your entire space-time motion into moving through space. At that speed, there is simply nothing left to power your journey through time. Your aging, your experience of duration, stops. The limit isn't a finish line you cross. It's the point where the needle on the cosmic speedometer points entirely to space, and the dial for time reads 0. The next time you look at a star, remember the reality of its light's journey. For that photon, no time has passed since it left its star. You are witnessing the end of a journey that, for the traveler, never even began. And by simply standing still, you are traveling through time at the fastest speed the universe allows. You, too, are riding the limit. Why the universe has a speed limit you can never break. Motion is fundamental to our experience of the universe. We see it in the slow drift of clouds, the orbit of the moon, and the silent expansion of distant galaxies. It has always been natural to ask how fast things can go. But there are rules to this universe, fundamental principles woven into the fabric of reality itself. And one of the most profound of these rules is that there is a speed limit. This is not a technological barrier, a problem waiting for a more advanced engine or a more powerful fuel. It is a core property of spacetime. The common explanation is that it takes infinite energy to reach the speed of light. And while this is true, it is not the complete story. The reason for this limit is more intricate and reveals a surprising truth about the relationship between space, time, and motion. To understand this cosmic law, we must look back to a time when the speed of light was still a mystery. It is a journey of discovery that reshaped our understanding of the universe, revealing a reality far stranger than our intuition suggests. This is the story of the ultimate speed limit, the historical chase for light's speed. For most of human history, the speed of light was considered infinite. Its passage seemed instantaneous. There was no perceptible delay between a distant event and the sight of it. The idea that light might take time to travel was a philosophical minority view, without evidence to support it. The consensus held that light simply existed, everywhere at once. The first observational challenge to this idea came in the 17th century, from the Danish astronomer Ole Romer. While observing the orbital patterns of Jupiter's moon Io, he noticed a small but consistent discrepancy. Io's orbit is regular, like a cosmic clock, disappearing and reappearing from behind Jupiter at predictable intervals. Yet, Romer observed that the timing of these eclipses changed throughout the year. When Earth was moving away from Jupiter in its own orbit, the eclipses of Io appeared to occur progressively later than predicted. When Earth was moving towards Jupiter, they happened earlier. Romer deduced that this was not an issue with Io's orbit, but with the travel time of the light coming from it. The changing distance between Earth and Jupiter meant the light had a longer or shorter journey to reach his telescope. For the first time, light had been observed crossing a finite distance in a finite time. Its speed was not infinite. Over the next 2 centuries, experiments were designed to measure this speed with increasing accuracy. But the true conceptual shift came in the 1860s, with the work of the Scottish physicist James Clerk Maxwell. He was developing a set of equations to unify the forces of electricity and magnetism. His work was not concerned with the nature of light. Yet, from his mathematics, a prediction emerged: the existence of electromagnetic waves. When Maxwell calculated the speed at which these waves should travel in a vacuum, he arrived at a number that was strikingly familiar: approximately 300,000 kilometers per second. It was the measured speed of light. The conclusion was inescapable: light is an electromagnetic wave. This unification was a monumental achievement in physics, but it raised a difficult question: 300,000 kilometers per second, relative to what? The speed of sound is relative to the air it moves through. The speed of a boat is relative to the water. Scientists proposed an invisible medium for light, a substance filling all of space they called the luminiferous ether. This ether was imagined to be the stationary background against which light moved. If it existed, then the measured speed of light should change depending on Earth's motion through it. In 1887, Albert Michelson and Edward Morley designed a remarkably sensitive experiment to detect this ether wind. Using a system of mirrors and split beams of light, they attempted to measure a difference in the speed of light traveling in different directions relative to Earth's orbit. They expected to find a small but detectable variation. They found nothing. The speed of light was exactly the same in all directions, at all times of the year. This null result was one of the most significant in the history of science. It created a quiet crisis in physics. If there was no ether, how could the speed of light be constant for all observers, regardless of their own motion? It would take a young patent clerk in Switzerland to assemble these pieces into a new picture of reality. Einstein's revolution. In 1905, Albert Einstein published his theory of special relativity. He did not try to explain away the strange result of the Michelson-Morley experiment. Instead, he accepted it as a fundamental principle of the universe. He proposed two postulates. First, the principle of relativity. The laws of physics are the same for all observers in uniform motion. This means there is no experiment you can perform in a closed, steadily moving system to determine if you are moving or at rest. There is no privileged, absolute reference frame. Second, the principle of the constancy of the speed of light. The speed of light in a vacuum, which we call c, is the same for all observers, no matter how they are moving. These two ideas appear to contradict our everyday experience. Consider an observer standing beside a railway as a train passes at 100 km per hour. If a person on the train throws a ball forward at 50 km per hour, the observer on the platform measures the ball's speed as 150 km per hour. Velocities simply add up, but Einstein stated that this does not apply to light. If the person on the train turns on a flashlight, they will measure the light moving away from them at speed c. According to Einstein's second postulate, the observer on the platform will also measure that same beam of light moving at the exact same speed c, not c, plus the speed of the train. This is the central paradox. How can a single beam of light have the same measured speed for two observers who are moving relative to one another? For both postulates to hold, something fundamental about reality had to be incorrect. Einstein realized it was not the behavior of light, but the nature of space and time themselves. For the speed of light to remain constant for everyone, space and time must be flexible. They must stretch and compress to ensure this one universal law is never violated. This was his core insight. He did not force light to conform to the rules of ordinary objects. He rebuilt the rules of the universe around the constancy of light. In this new framework, c is more than just a speed. It is the speed of causality itself, the maximum rate at which any effect can propagate from its cause. To break this limit would be to violate the logical structure of the universe. Our clocks and rulers were not the rigid, absolute instruments we believed them to be. Their measurements are relative, and the consequences of this idea are deeply strange. The bizarre consequences, time dilation and length contraction. Accepting Einstein's postulates forces us to abandon our intuitive notions of space and time. The universe engages in a strange dynamic to uphold the constant speed of light, a process most clearly seen in the phenomena of time dilation and length contraction. Consider a simple, light clock, made of two parallel mirrors with a photon of light bouncing between them. For an observer holding this clock, each time the photon strikes a mirror is one tick. The photon travels a short, direct path, up and down. Now, imagine this clock is on a spaceship moving past a stationary observer at 80% of the speed of light. From the stationary observer's perspective, the clock is moving sideways. For the photon to travel from one mirror to the other, it must now cover a longer, diagonal path. The critical point is this: both observers must agree on the speed of the photon. That speed is c. But from the stationary perspective, the photon travels a longer distance for each tick of the moving clock. Because speed is distance divided by time, if the distance is longer and the speed is fixed, the time must also be longer. This means that, from the stationary observer's viewpoint, the clock on the spaceship is ticking more slowly. This is not an illusion or a mechanical error. Time itself, in the moving reference frame, is passing at a slower rate relative to the stationary frame. This is time dilation. The faster an object moves through space, the slower it moves through time. This effect is not theoretical, it is a measurable reality. The clocks on GPS satellites run slower than clocks on the ground due to their high orbital speeds, and this relativistic effect must be accounted for to prevent navigational errors. Just as time stretches, space must contract. Imagine a journey to a star 10 light-years away, as measured from Earth. An astronaut travels at 99% the speed of light. From Earth's perspective, the journey takes slightly more than 10 years. For the astronaut, however, time dilation means their personal experience of the journey is much shorter, perhaps only a little over 1 year. This leads to a paradox. If the astronaut experiences a 1-year journey at nearly the speed of light, how can they have traveled 10 light-years? The answer is that, from the astronaut's perspective, the distance itself has changed. The 10 light-years of space between Earth and the star has contracted in their direction of motion. To the traveler, the distance is shorter. Space and time are not a fixed background. They are dynamic, stretching and shrinking in a precise relationship that preserves the one constant: the speed of light. This is why the speed limit cannot be broken. Reality itself warps to prevent it. And there is one final consequence of this warping: the relationship between energy and mass. The energy barrier, E equals mc squared. The warping of space and time gives rise to another barrier, one related to energy. This is described by Einstein's most famous equation, E equals mc squared. The full relativistic equation includes a term known as the Lorentz factor, represented by gamma. This factor, calculated as gamma equals 1 square root 1v squared c squared, governs the degree of time dilation and length contraction. When an object is at rest, v equals 0, gamma is 1. As its velocity, v, approaches the speed of light, c, the denominator of the equation approaches 0, and the gamma factor increases toward infinity. Einstein showed that the effective mass of a moving object, its relativistic mass, increases with its velocity. The total energy of a moving object is given by E equals gamma mc squared, where m is its rest mass. As velocity increases, gamma increases, and therefore the total energy required to sustain that motion increases as well. Imagine applying a constant force to a spaceship. At low speeds, the acceleration is predictable. But as the ship's velocity increases, the same amount of applied force produces less and less acceleration. From an outside perspective, the ship's inertia is increasing. It is becoming more resistant to changes in motion. As the velocity gets closer to c, the gamma factor begins to rise dramatically. Each increment of speed requires a far greater amount of energy than the last. As the velocity, v, approaches c, the gamma factor approaches infinity. Consequently, the energy required to accelerate the object also approaches infinity. To make any object with rest mass reach the speed of light, an infinite amount of energy would be needed. The universe does not contain infinite energy. This is why the speed of light is a limit only for objects that have mass. Particles of light, photons, have no rest mass. Because their mass is zero, they are not bound by this energy requirement. The theory dictates that massless particles must travel at exactly the speed of light, never slower or faster. The idea of an infinite energy requirement is not an arbitrary rule. It is a direct consequence of the fundamental geometry of spacetime. It is the final barrier that emerges from the relationship between space, time, and mass. The cosmic test, expansion versus the limit. The speed of light is a local limit. Nothing can move through space faster than c. And yet, a phenomenon on a cosmic scale seems to challenge this rule: the expansion of the universe itself. In the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This is not because the galaxies are flying through space like projectiles. It is because space itself is expanding. The common analogy is a balloon with dots drawn on it. As the balloon inflates, the rubber surface stretches, and every dot moves away from every other dot. A dot that is twice as far away appears to recede twice as fast, because there is twice as much expanding rubber between them. The universe works in a similar way. The expansion rate is described by the Hubble constant, which has a value measured to be around 70 km per second per megaparsec, a distance of about 3.26 million light-years. This means that for every megaparsec of distance between two galaxies, the space between them stretches at a rate of 70 km per second. Over vast cosmic distances, this expansion adds up. A galaxy that is 100 megaparsecs away recedes at 7,000 km per second. At a certain distance known as the Hubble horizon, about 14 billion light-years away, the total expansion of space between us and a galaxy at that distance means it is receding from us at the speed of light. Any galaxy beyond that horizon is receding faster than the speed of light. This appears to be a violation of Einstein's limit, but the reason it is not is subtle and important. Special relativity states that nothing can move through space faster than light. The galaxies receding from us faster than light are not traveling through space at that speed. They are being carried by the expansion of space itself. An object in one of those galaxies would not be violating any local laws of physics. Light in that galaxy would still travel at speed c relative to its source. The rule that no two objects can pass each other locally faster than light remains intact. The expansion of the universe does not break the speed limit, it clarifies its nature. The limit applies to motion within spacetime, not to the behavior of spacetime itself. The philosophical implications, light's eternal journey. We have explored the physics, from historical observation to the consequences of relativity. But the nature of this universal limit extends beyond equations. It touches upon the structure of existence itself. Consider a single photon, emitted from a star a billion light-years away. From the moment of its creation, it travels at exactly 299,792,458 meters per second. For billions of years, across expanding space and past gravitational fields, its speed does not change. According to the mathematics of relativity, for an object moving at the speed of light, time dilation is infinite. This means that for the photon itself, time does not pass. From the moment of its creation to the moment it is absorbed, the journey is, in a mathematical sense, instantaneous. It experiences no duration. Its beginning and its end are simultaneous. The photon is a timeless messenger, connecting the deep past with the immediate present without aging. In a universe where stars die, galaxies collide, and space itself expands, the speed of light is a fundamental constant. It is a democratic law, the same for any observer anywhere in the cosmos. It is a shared reality. This limit also defines our relationship with the universe. Light connects us to the past, allowing us to see the echoes of the Big Bang and the birth of galaxies. But its finite speed also isolates us. The light from the nearest star is more than 4 years old. We are always looking into the past. In a way, the speed limit is a constraint. It suggests that without some undiscovered physics, travel to other stars may never be practical. The universe is simply too vast. Yet this constraint is also what gives reality its structure. A universe without a speed limit would be a universe without a clear sequence of cause and effect. It would be a place where everything could happen everywhere at once. The limit is what allows for a universe with history, with structure, and with the capacity to be understood. The deepest answer to why the universe has a speed limit is that the limit is not about speed alone. It is about causality. It is about the fundamental geometry of space and time. The speed of light is not a barrier to be broken. It is the rule that allows the game to be played at all. Conclusion. We return to the original question. Why can you never break the speed of light? It is not simply a matter of energy. It is because reality is built on a foundation where the speed of light is absolute. To uphold this single fact, the universe alters the very nature of space and time. As an object with mass approaches this speed, its experience of time slows, space contracts in its direction of motion, and its resistance to acceleration increases toward infinity. It is a limit enforced by the geometry of spacetime. Even the apparent faster-than-light recession of distant galaxies is not a violation of this rule, but a demonstration of its scope, a law governing motion within space, not the motion of space. In the end, the speed of light is more than a number. It is the pace of causality. It is the one constant in a universe of change, a timeless connection between the past and the present. It defines the boundaries of what is possible. And in that constancy, we find a deep and elegant order. If this kind of calm exploration into the fundamental nature of our universe helps you think, consider subscribing to the channel. Thank you for watching.